Hi there, welcome to the Data Pipelines with Python course. In this course, we'll be taking a look at basic data pipelining concepts, as well as practical use cases for data pipelines using Python. We'll cover some of the more popular task and data workflow tools, including Celery, Luigi, and Airflow, and touch on some of the overarching concepts when building a data pipeline. By the end of this course, you should feel comfortable assessing if a pipeline framework is right for your project. You will have some experience comparing pipeline tools and writing tasks in Python. You will also have some experience working through parallelization of data and work. Finally, you'll have a greater understanding of how to approach data pipelining with a Python toolset. In order to do this, I'm going to again be focusing on the larger concepts, and I'm assuming that you'll be able to take these threads and apply them to whatever workflow you need to build. Of course, we won't have time to cover everything, so consider this course just the building blocks. The course code is all located at GitHub, at my KJM Data Pipelines course GitHub repository. I have also included some homework and solutions for you along the way. However, I expect you will learn far more by applying the concepts we cover and the frameworks we cover to real data use cases that you have. As far as local setup is concerned, you will be in charge of making sure your system has the proper libraries installed. The repository README instructions is a good first place to start, and I've included some requirements.txt and conda YAML files to get you up and running. As with most Python setups, if your local setup has some particularities, I'm happy to help debug if you reach out on GitHub or Twitter. But you should also feel comfortable enough with systems to have a look on your own. In this course, we will be doing some more intensive installation than most Python courses, because data pipelines means some systems work. So even if you have no experience debugging system errors before, you likely will by the time you finish this course. Everything in this video series will be in Python 3, with the exception of the Ansible scripts, which at the time of this recording are not yet ported. That said, if you're using Python 2 with some future imports for Unicode literals and print, you should be able to follow the same course without issue. Of course, if you do have an issue, please reach out via GitHub, and I'm happy to help. I'm really excited to get started, so enough chatting. Let's build some pipelines. Why automate? In an era where humans are doing less and less and machines are doing more, this is still a question in some offices and industries. Fear we will lose our jobs to machines wanes when we think of automation as an aid in the process of our work rather than a replacement. Here's one way automation helps our lives. With apps like If That Then, which allows us to program things like turning our lights on at sunset, we can automate our houses, conserve energy and time, and spend more of our life doing the things we enjoy rather than monotonous work on simple tasks. What if I told you the 4 hours you spent towards data processing might be reduced or even skipped using automation? With tools available today, you can help speed up your data processing and follow the write it once and forget it mentality we programmers know and love. But automation doesn't fix every problem and does indeed create its own set of work. As we'll learn throughout this series, automation can sometimes create quite a lot of new tasks to monitor and review. We should ask ourselves, what works well with automation and what works poorly? This will indeed vary based on the tasks and data you handle daily or quarterly or yearly. In general, there are some obvious situations where automation lends itself and where we can see automation might not be worth it. This is a table based on a table in a book I co-authored with Jacqueline Kazel called Data Wrangling with Python. You can see that some tasks are really obvious for automation, if there's clear success and if you can retry when you fail, whereas others that might require human intervention or are more one-off reporting, they might not be good tasks for automation. There are some tasks which might be hard to automate as a whole, but lend themselves into being broken down into smaller tasks, or what we might refer to as subtasks. When approaching automation naysayers, or say you are feeling yourself as if it might be impossible to automate a task, try and determine if there are smaller steps which don't require humans. Finally, as you prepare to automate, it's important to come to a clear picture of what your task and endpoint look like. You might want to ask yourselves as team lead or junior or senior dev, or as an entire data team, specifics about the exact task at hand, the necessary results, and how to help guarantee success for your automation. It's easy to write a script that works once. It's much harder to write an entire system of tasks that will succeed often and fail without impacting the entire team or company. Here listed are a few more questions from our book. There are some good first steps in terms of figuring out how and what to automate in your data pipeline. I look forward to walking the path of automation and data pipelining with you. Let's begin. In this video, we're going to cover how to set up your first server. If you're a seasoned sysadmin, you can skip this video. However, if you have never or rarely worked on servers, this video will take you through the steps of getting started as a server admin. Why do I need a server, you might ask? Part of learning about automation is also learning how to automate across several machines, or at least one that's not your usual laptop. Although many of the systems we will learn about in this series can be run on one machine or on a machine with several virtualized machines, you should feel comfortable launching servers and working on them. Throughout this video, we'll be using bash commands. If you want to learn more bash, there are plenty of great resources online. Jacqueline Kazel and I also wrote an entire appendix on this in our Data Wrangling with Python book for O'Reilly. Some of the steps in this video are covered in Brian Kennedy's awesome article on security for Linux servers. I have it up here, my first 5 minutes on a server. I recommend taking a read. To begin, we first need to launch a new server on the cloud provider of our choice. I usually use DigitalOcean, so that's what I'm going to use here. If you use another service, the steps should be similar. I'm going to go to Create Droplet, and I'm going to use a Debian server. I'm going to choose a smaller size for now. I can resize later. And you should choose a data center region either near you or near the team you're supporting. Since I'm in Berlin, I'm using Frankfurt. You can select additional options, and then DigitalOcean has my saved public keys, so I can automatically log in. You should have a public and private key pair from working with GitHub or other services that use keys. If you don't have a key yet, take a look at how to generate SSH keys for your operating system. For Windows users, you'll need to install PuTTY. Remember, never share your private key with anyone. Since I'm on my Mac, I'm going to use my Mac key. And then I like changing my host name so that I remember what server I'm on. Okay, so now that my server is launched, I have this IP address. Depending on if you're using a different service, which might have sent you a password or gave you a key to download, your login might look different. I'm going to copy this and launch a terminal window. Let's maximize this. So in order to use my SSH key, I'm going to need to source my bash RC because I have my SSH add in there. You want to make sure that your SSH key is set up and registered for your user and located in your SSH folder. You can look up instructions for your operating system. Okay, so I know that DigitalOcean sets me up as a root user, so I can use SSH with the root login. And I want to say yes. And now I can see with a new shell that I'm in my server. I can also see that I'm the root user. Although this is great for sudo installation and other root user purposes, you normally don't want to remain root user forever, and allowing root login has security implications. The first thing we'll do as root is install failed to ban, which will ban users with faulty logins after a certain number of attempts. If you're using Debian or Ubuntu, you can use apt-get. For other operating systems, you might use yum or a different installation. And I'm going to say yes, I do want to continue, and it'll go about installing. Next, I want to create a new user that has sudo privileges. Sudo privileges allow us to do things like install packages, restart system services, and do other things that we might need as data pipeline experts. I'm going to use the add user command, and it's going to ask me for a new Unix password. These you can fill in if you'd like. I generally skip them. So we can see that we have a new home directory, and that it's set up for a good bash login. What we will need to add is an SSH directory. And we want to copy over the authorized keys from our root login to our deploy user. This makes sure that we can log in with SSH. Then I'm going to change some permissions. So first I'm going to make sure that only the owner can read the SSH file and execute on it. And then I'm going to make sure that the deploy user owns the entire directory. This is because I moved some things over as root user, and I just want to make sure that the deploy user has access to its own directory. Finally, I want to add sudo privileges. I can do so with the vsudo command. And here, I just want to add a line for our new user underneath the root user. So I can add a line here, and it's just going to look exactly the same as the line before. Save the modified buffer and exit. So now we're going to turn off SSH root login and test our new deploy user. I can do so by editing the sshd config file. So here you can see a lot of the different SSH settings. If, for example, you needed to change protocols or ports, you can do so here. What I'm worried about is this permit root login. I want to change this to no. If you're new to Vim, you need to press I to insert or edit the file. Then I'm going to explicitly say that password authentication is not allowed. This means that no clear text passwords and keys only can be used. And then I can actually add a line. I usually try to do so at the end. And I can actually declare what users can log in. You may or may not need to do this if you're using a server with a lot of different users. Okay, then I can press escape, :WQ. That will write it for me. If you want to learn more V, I recommend Vim Golf. It's really great and fun. So now I need to restart my SSH. I can do so by typing server SSH restart. And now I can test if I can log in with my new user. So I'm going to create a new tab. I'm going to source my bash file. And I'm going to try to log in with my deploy user. And I can see I'm there. I can check out my files, and everything looks great. I could also exit and try to log in with root. I should be banned now. I'm going to use the up arrow, change this to root, and my permission is denied. Excellent. So there are a few more steps in Brian's suggestions, and there's a lot of other steps that you can do to increase security even more depending on your setup. But at this point, you've done quite a lot more than most of the internet to add some security to your server. You also have a new user you can use for your data pipelining and automation. We'll be using this server and user throughout the course, so stay tuned. Having a server is almost like having another computer. Would you abuse your own laptop? I certainly hope not. You should extend the same care and attention to your servers. Some of the best practices in terms of taking care of your systems are also the best practices as an application developer and maintainer. I don't have time to go over every point in the 12-factor app listed here on this site, but if you haven't read it, you should. And if you don't follow it, then the onus is on you when something breaks or is hacked or simply doesn't work right from the start. An old friend and coworker of mine, Charles Hooper, wrote a great list on his blog called Operator Requirements. These are practices we should think about as developers or data engineers. A brief summary of what he's saying, although you should read it, is that your application or pipeline, or in our case automation, should be well logged, understandable, and documented. When it fails, there should be many indicators, including monitoring and alerting systems set up so your systems team and developers are aware of the failure. To do so, you can use a tool like GetSentry or Datadog, or really any other tool that does monitoring and alerts. There are many open source and commercial tools available to monitor and alert for systems errors, load issues, memory issues, or anything else that can happen to your server. It is not enough to monitor just your application or just your server. You should be monitoring and alerting for both. One easy and free tool is using the New Relic Free Monitor. It's fairly easy to install and it gives you some basic views into activity on your server. Similar to your application logging, you should be sure to only alert, especially in an on-call or pager duty sense, what really matters and not every single possible error. Those are in your logs and you can catch them later. Charles also points out that there should be some resiliency within your application to allow and account for graceful degradation so that small errors don't become larger ones. This also allows for changes in deploys to work without a breakage in service. It reminds me of the scene in Monty Python, where the Black Knight doesn't stop fighting even when he has no arms and legs. Your app shouldn't either. Build an app or a pipeline like the Black Knight. If you are maintaining your own servers, or if you are helping in a DevOps role as you deploy new services to your company's servers, then it is essential to learn some of the basic terms of system caretaking. Generally, you should be aware of simple debugging given the server's chosen operating system or architecture. Julia Evans writes some interesting posts on Linux debugging. You should check out her blog. If you are using containers, you should read more on how they work and connect and the underlying architecture. If you're using virtual machines, understand some basics of hypervisors. If you're using containers on virtual machines, you should probably learn about both. Set up monitoring to view how your containers or virtual machines are performing and what's keeping them busy or not. You should be considering latency, network performance, queries per second from and to both upstream and downstream containers or systems. You should also be checking the workload of your current containers, including disk, memory usage, as well as CPU. Datadog has a great article on container monitoring and the Docker monitoring problem, as they so put it. If you're in the cloud rather than using dedicated hardware, understand the issues of cloud systems where you're sharing a box with others and therefore dealing with resource throttling and sometimes noisy neighbors. You should be prepared to scale in light of these limitations. Amazon and several other providers have autoscale options, but pricing of new available instances can vary and should be considered when budgeting for autoscaling. Regardless of operating system or deployment, or even if you aren't in charge of the servers your code runs on, you should know how Python data types and compilation work and how whatever storage you are using operates on a systems level. Making decisions with performance and maintainability in mind is a key part of ensuring your code doesn't break the system it's designed to run on. Performance testing your code is essential, particularly for large data solutions. There's a good talk by Dan Crosta from Hacka Labs that you can check out here on YouTube. There's also plenty of other great books for high-performance Python. Just as you did with your code and application or automation and pipeline, you should set up testing for your system, including both integration testing, such as do my recent changes break things, as well as code unit tests. Does my code perform as it should? Many larger systems use continuous integration with tools like Jenkins, so each release can be tested before it's in production. These types of systems can also allow for an easy small audience testing, so only a small segment of your current production is tested with the new code. Then you can roll back to the old system if there's a spike in errors. Not being afraid of testing your containers or your virtual machines should be a given. Finally, having a somewhat mirrored development and staging environment allow your team and yourself some breathing room. It's not always possible to remake the entire architecture of production, but you should aim to have a good testing and monitoring so you know whether a recent change in code or automation will cause any disruption or pain for your production stack before it's released there. If you absolutely need the change and it means that you need to scale production, make sure that your plan for scaling your production footprint is planned and tested in advance. In these instances, load testing is essential. One of the great tools is Twitter's Iago. So the basics we've covered in terms of being a good systems caretaker is monitor everything, test as much as you can, understand how the architecture works and the system works, write and understand performant and flexible code, and above all, be nice to your sysadmins and your servers. We're going to be talking about what a queue is today. A queue is a computer science abstract data structure, which allows you to add, remove, or release, and store tasks or messages or data in an intermediary data structure or database for later handling. Queues are often used in automation to allow for a distribution of work, meaning if I have one central queue, I can set up many different computers or processors to pull work from the queue and perform work concurrently. This means I've also freed up the processes who are inputting the work so that they can go back to their original work as well. When we think of queues, we think of long lines, like at the register of an understaffed grocery store. The good news is, in computers, we can have this long line, but we can easily open more checkout lanes. But similar to the store, we must be aware that these extra workers will cause extra overhead, and we must be aware of how long the line is getting. Depending on how you want to build your queue, you can have many different types of tasks, and you can have a distributed queue which is available across many machines. You can also determine if your queue operates by taking the oldest, stack implementation, or newest, sometimes called first in, first out. We can see here that we have producers in queuing into a queue or a stack, and then we have consumers dequeuing. If it's first in, first out, it's going to take the most recent task rather than the last or end one. Your queue can also help determine when to expire a task or when to flush tasks. You can set up priority queuing or ways that your queue works to skip the line. There are many technologies used for queuing across languages, but some of the more popular ones you might have heard of are messaging queues, such as RabbitMQ, Amazon SQS, ZeroMQ, and Apache Kafka. Additionally, many lightweight databases such as Redis or MongoDB can be used for queuing. Sometimes people implement queues using normal databases or distributed databases like Cassandra. and this usually ends up not as successful. Regardless of the technology you choose for your queue, the theory of queuing and the decisions you make about what and how to queue are going to influence your application's design and automation architecture. Take time to read and think about what types of queues might work best for your structure and what you intend to queue. Remember, your queue might end up being a primary structure within your application stack as it grows, so spending some time now to make good decisions can pay off later. Today we're going to talk about producers and consumers. Producers and consumers are essential pieces of queues when it comes to computer science. The producer creates new work to enqueue, and the consumer is in charge of performing the work and dequeuing. The important idea is that we need both of these processes or workers in order to have a functional queue. So a producer is any of the workers or processes that add to your queue. This can be something linked to your web application, or this can be something linked to your data pipeline. So you can imagine all of your log data coming in, you'll need those producers adding to the queue. The consumer is the workers or processes that remove tasks or data from your queue. You can think of these, again, as something that's taking away from your data pipeline and doing the processing on the data. This can then essentially save it to a database or whatever data structure you're going to use for your data science team. You can imagine several issues with producers and consumers that might arise. First, what if I have only one consumer and several producers? What might occur? That might lead to a full queue or a very long queue that might never finish without intervention. And what if I had several consumers and only one very slow producer? We would have consumers waiting around for work that's not there. Monitoring our queue and the busyness of our producers and consumers can help alleviate these problems. If we know our queue is growing and our workers are very busy, we can add more consumers, helping keep up with the speed of the producers and the queue growth. Alternatively, if we know that we have many idle consumers, we can decrease their count, or we can add more producers depending on our needs. The tools we'll cover in this series will give you some insight in monitoring into your queue, and there are even ways to automate consumer and producer counts, so no need to fret. Understanding that these worker types exist and that they must be monitored and set are a part of learning about queues and automation. You might ask, why use Celery for your automation? Celery is one of the oldest and most widely used Python tools for automating tasks and working with queues. It reached 1.0 in early 2010, around the time I first used Celery, and is now in the 4.0 release. It's well maintained, it's used by many, and it has great documentation. What's not to like? On top of widespread usage and support, it's simple to learn and easy to switch out different architectures if and when your needs change. It works with both scheduled and event-driven automation, allowing you to turn any Python function into a task. You can use it easily with RabbitMQ, Redis, and several other backends. Here's a list of all of the different supported brokers. It also has great settings to enable logging, retries, as well as task chains. If you're using Django, it has a built-in plugin support. If you're migrating from a cron-based task or script, it also has a scheduler, which allows you to essentially recreate cron in a distributed queue environment. You can even set up separate queues with varying priority or consumers, allowing you to more fine-tune control your system. You can also install a great additional monitoring library called Flower. This allows you to have a visual queue, as well as view tracebacks or errors and long-running tasks in a browser. Here's an example screenshot. Finally, because it has such widespread usage, there are many use cases that have been explored and documented. For example, on the Celery project homepage, they document that Instagram, Mozilla add-ons, and AdRoll are all using Celery. If you need a simple asynchronous queue or you're looking for an easy migration from a cron or callback-based task setup, Celery is for you. To best understand how to set up your Celery system, we need to understand how it's architected. We know it uses producers, consumers, and a messaging queue. Celery is in charge of scaling the consumers, managing the tasks the consumers perform, as well as sending data to the messaging queue and pulling that data when the task is running. Here's a great diagram from the O'Reilly book, Parallel Programming with Python. And we can see that Celery is here, managing the message transport and these workers. It's also writing back-end results and might send those back to the client depending on your task. And we see these clients are then producing more tasks for our task queue. Celery uses a series of libraries that can talk to the messaging queue and run in Python. Celery calls these brokers. When you install Celery, you can use it with a variety of messaging queues or backends, ranging from popular libraries like RabbitMQ and Redis to lightweight databases and NoSQL data stores. Here's just an example of some of the brokers. Be aware that not every broker comes with the same features. As you can see from this chart, not every broker has the same monitoring or remote control support. If you're a fan of one or more of these brokers, consider contributing to Celery by helping build additional features. Celery runs with an application instance, which can be set up with several configuration options. There's a great list of all of the different configuration options available on the Celery documentation site. Depending on your setup, there may be some options that you want or need to set, such as concurrency, time and date, as well as logging and error alerting. You will also need to specify your message broker and your result backend if you plan on storing your results to a database or message store. To begin, we're going to install Celery locally. So I'm going to go to my terminal. So first, we're just going to install it locally. You'll want or need to run through these steps via a server, and we're going to go over that a little bit later in this chapter. So locally, I use virtual environments. I'm going to use Python 3 since Celery supports it. The commands will be the same for Python 2, but you won't need to specify which Python for your virtual environment. If you don't yet have virtual envs, please follow the instructions in the README to install. I personally like using virtual env wrapper, so that's what I'm going to use. But if you're familiar with the virtual env commands, you can use those as well. So as we can see, this is going to go through and make a new virtual env data pipelines with Python 3. Now I've created the symlink that points to user bin Python 3. If you want to know where your Python 3 lies, you can type which Python 3, and that should tell you where it's pointing to. Right now, since I'm in a virtual environment, it's pointing to the Python 3 in my virtual environment. But if you're on your system outside of a virtual environment, it will show there. Now we can use pip to install Celery. We'll be using the RabbitMQ backend since it has more features and is widely supported. If you don't already have RabbitMQ installed, you can follow the instructions for your operating system on the RabbitMQ website. Since I have Homebrew on this Mac, I've already installed it, but I could install it again by typing brew install RabbitMQ. And we can see that it's already installed. Now I can use pip to install Celery. I want to specify that I would like to install the RabbitMQ version. There's a great listing on the documentation if you want to use a different backend. To install the extra libraries for RabbitMQ, you merely need to put open and close square brackets with RabbitMQ following Celery, like so. And here we see some of the transport and multiprocessing libraries that help Celery function. It's using things like AMQP and Kombu to manage the messaging queue confirmations, and using Billiard to do things like concurrency. I also want to install some extra libraries that we'll be using. These include Pandas and Jupyter for our data work. We're going to be using some financial information, so I'm also going to install the data reader, and I'm going to install Jupyter. Before I end this, I also want to set up a user and a virtual host for my RabbitMQ. This is so that if I'm using RabbitMQ with a few different applications, I know which ones are tied to which applications. I can use the RabbitMQ control commands. Now, if you've brew installed or a different way, you may need to follow specific commands after you install to get these in your command line. For example, you may need to link your sbin to your bin so that these commands show up in autocomplete. You can follow the instructions easily on the RabbitMQ homepage. So I want to call RabbitMQ control, and I'm going to add a user, and I'm going to pass the username and the password. My Celery user and my best password ever. Now I need to add a new virtual host so that when I connect, I'm connecting just to that virtual host. And now I want to give my user permissions to that virtual host. All right, so now I have my user set up and my virtual host set up, and I also have all of the libraries I need installed. So we can move on to building our first tasks. Okay, so at this point in time, we have Celery installed and running, and our RabbitMQ is running. Now we need to get some tasks set up. Celery workers run within a Celery application, We need to both define some tasks as well as our Celery application with configuration to get our Celery project started. To begin, I've set up this new file called task.py. I'm in my text editor, Atom, and here I just have a simple task. To define a new task, I simply need to write a new Python function. I can then use a special decorator to make it into a task. Usually, I test my tasks as functions first before adding the abstraction layer of a task. I thought it would be interesting to build some tasks around Pandas data reader, which can be used to pull financial stock information. Here, I've written a simple task that pulls some aggregate data of a stock over time. So if we just read through it really quickly, it's called get stock info. I'm passing it something called stock start end. There's further documentation of this within the repository and the working files, so check there. Then I have a keyword argument called source, and here's equal to Yahoo as default. So I'm creating a new data reader object, and that's going to essentially return a data frame for me from whatever financial query I have. So I'm querying with the stock, the source, and the start and end dates. Then I'm setting a new column called stock equal to the stock symbol. That's what's passed there. And then I'm creating an aggregate where I'm grouping by the stock and I'm creating aggregates of the open, adjusted, close, close, high, and low columns, which are all of the columns returned. Within those, I'm passing some features that, if you're familiar with pandas, should be obvious to you. The minimum, maximum, means, and medians of each of those aggregate columns. If you need to learn some pandas, I actually do have an O'Reilly video called Data Analysis and Wrangling with Python, so I recommend checking it out. In line 13, I'm changing the column names so that instead of being multi-level hierarchical columns, which look a little bit weird in JSON, I'm just making them flat strings. So essentially, it will have something like open minimum, open max, and so on. Then I'm returning that aggregate data frame to JSON. So first, we want to make sure that we test the function. I'm going to hop into IPython and test it. So here I'm in that same directory, and I'm just going to hop into IPython, and I'm going to import my get stock info from my tasks. And now I just want to try it out. Now the other thing I need to import is datetime, because what I need is datetime objects passed. So let me do that as well. And say I'm curious about Facebook stock. Let me take a look. I'm going to say my result is equal to my function name, the symbol for Facebook, which is FB, and then I need to pass a start and end date. So I'm going to say starting the 1st of January in 2016 and ending today. Now I can check my result, and I can see it is a JSON string. So my function works properly, and it's returning and aggregating in a proper way. I might want to clean up some of this JSON because I don't really need FB as every single dictionary, but it's looking pretty good for giving me some basic details that I can go through with the JSON parser. So now I need to get my Celery app defined. I'm going to go back to Atom and do it there. So I've created a new file called Celery app, and you can see I just have one simple import. We need to import the Celery object from the Celery module. Then what I can do is I can pass it a name, as well as the broker and the backend. And we can see here that this is the Celery user with the password at localhost at port 5672, and I'm going to use my vhost that I set up. Now, if you didn't bother setting this up, you could use guest without a vhost name, and that's going to work on nearly every RabbitMQ install because it installs that user with a guest password. Then I'm setting my backend to that same AMQP, and that's going to allow me to look at the status and make sure that my task succeeded or failed. Now that I have this app defined, I can go back to my tasks and import it. So I'm just going to import it, and then I'm going to add a decorator to my task. And that should be all I need to do. To check if it's working, I can start and run a simple worker. I need to do that in my terminal. So what I'm going to do to start that, I need to make sure I'm in the right folder, which I am. I need to activate my virtual environment with Celery installed. So now that I'm in my proper virtual environment with Celery, I can simply type celery. I'm going to do -A, which is going to point to the task file to load. It's called tasks because it's task.py right in that same folder. Then I'm going to tell it to start a worker with the log level of info. This should give me a little bit more information of what tasks it sees and how many workers are running. So you should see something like this. We can see that it has my app listed, it has my transport listed, it has my results listed, and it has some concurrency. We can also see that it's using the Celery queue and the Celery exchange. These are the default queues and exchanges. We'll talk about how to set up different ones in a different video. Then I can see down here that my task is loaded with get stock info. So now I should be able to call this task with delay. So what I'm going to do is I'm going to start a new IPython. So now I'm going to import my same task like before. I'm going to need to import datetime as well. And now I can set my result and pass those same commands. And I can see my function still works that way. Now to run it as a task, I need to pass the arguments with the delay. So what I'm going to change here, I'm going to add this dot delay, and I'm going to pass it with all the arguments as delay. And when I run that, I can see that I now have an asynchronous result. If I go to my other window, I can see that my task has now succeeded. It's received and succeeded. If I go back and check, I can see my status. I can use the info command to get the data. I can also simply call .get, which is going to return the data. And I can check things like, did it fail? So when we're done, we can stop our worker by hitting Control or Command C in our worker window. In the code repository for this video, you're going to find a few more tasks, and you're also going to find that the tasks that we built today are further documented. I challenge you to add at least one more task. For example, how about showing the year-over-year change of a stock just given its symbol? Or you can write a task to take a look at earnings per share via the Yahoo API. I've included some examples in the moretasks.py file, but try doing it yourself without peeking. Getting your tasks on your server and running properly is an important part of having a functioning distributed task queue. In this video, we're going to take a look at how to do this in a simple way. If you're using Ansible, Fabric, Puppet, Chef, or any other automation framework, you can follow these same steps using that automation, but you'll need to write out the scripting yourself. I encourage you to learn at least one automation framework, but that's beyond the scope of this series. We'll be using an Ansible playbook and Ansible to deploy to our server. I've included an example playbook in the repository, but you don't need to use it. So the script uses a set of instructions for our server about what packages to install, as well as how to pip install the requirements. It then pushes the code to the server. So in order to use Ansible, we first need to pip install Ansible. And if you're using Python 3, then Ansible doesn't yet support Python 3 at this point in time. The good news is we can still use Ansible to deploy and install Python 3 programs. We just have to install Ansible itself in a Python 2 environment. So to do so, I'm going to go back, and I've actually created a virtual environment already that has Ansible installed. I can try pip installing Ansible again, and everything is already there. And we can see from the output that it is using Python 2.7. So it's using the default Python on my system. So the first thing we'll do is we'll take a look at the Ansible file itself, the playbook file. It's included in the deploy folder. So I can open it up. We want to take a look at the playbook file. So we can see here that we have a normal YAML file, and it has a lot of different arguments. This file is quite long, and normally I like to break up my Ansible into different roles and have them all in different folders. I made this just as an easy example for you to use, but I highly encourage you, if you're using Ansible or if you're interested in learning Ansible, to take a look at roles. That allows you to pull out some of these different pieces and keep them in smaller modules. Then you can have a normal playbook folder, and that can call all of the different roles that you need to install on the server. I highly encourage you to read through the Ansible documentation and learn more about them. We also see that we have an include variable. I've included a file for example variables here, and we see we're going to need to set these variables. Some of them are just going to be your domain name and your email, but we also need a SHA-1 password and a plain text password. For this Ansible playbook, I'm going to use Jupyter Hub, which is a neat Jupyter notebook project that allows you to have multiple users run their own notebook environments. I encourage you to check it out if you're working with a team who use their own notebooks. To use Jupyter Hub, you have to have an SSL certificate and a domain. These are some of the variables along with the password. For your purposes, you will need to modify this playbook and install maybe only a few things or change some of the packages used. This is meant as a guide so you can start automating your deployment, not as a playbook that can be used by every student taking this course. You might not want to use Ansible right now and instead install RabbitMQ and Celery directly on your server, similar to how you set it up locally. If so, I recommend setting up a simple Git remote endpoint and pointing it to a folder on your server. That way you could do a simple Git push from your local repository to deploy new tasks to your server. You will also need to manage restarting Celery at that time. So let's go back to our shell so we can run our Ansible script. Ansible runs off of a series of hosts. You can configure them in a file that's usually located in etc. Ansible hosts. We can take a look at mine. We can see I have a pipelines group, and then I have the information for my pipelines user, which is using the username deploy, and that's my IP address. To run the playbook, I'm simply going to use the Ansible playbook command. And I've used the ask sudo pass command. That's going to ask for my deploy user sudo password and is a great tool to make sure that your user still has a secure password, but you can also run your playbook with sudo. And the playbook's going to run through and it's going to likely not change a lot because I've already set up my server. If you run into an error, you're likely to do that the first few times that you use Ansible. Then try to look at the output. Ansible is really good at giving you the output directly from the command, and you can usually debug from there. It might be just that you're missing some files, or it might be a permissions error. Whatever it is, just try and debug it from there. So now that it's done running, I can go to my server that's set up, and I have it set up at pipelines.kjamistan.com. Here I can see that it's asking for my deploy password, and then I can log in to my Jupyter Hub. So now I can create a new notebook. Since our tasks are in the var www pipelines folder, which is a deploy endpoint for our repository, I'm going to add that to our system path. Now I should be able to import the tasks. I'm also going to import datetime. And now I can call my task. And I can see that my task has succeeded, and I can get the results of my task. Super, so now we have our tasks deployed on our server, and we can easily share them with our team or others who need to use our Celery code. Again, Jupyter Hub is a great tool, but it runs as the root user, so you want to make sure you only have benevolent actors working on your notebooks. That said, it's great to be able to have your team use one or more computers for performing data pipelining work and utilize the power of Jupyter Notebook to analyze the tools you are building with Celery. When we think of distributed task queues, we think of many different servers or machines running large-scale queues with a variety of priorities and inputs. For Celery, scaling your tasks and workers is pretty simple. In this video, we'll cover how to scale Celery along with scaling your tasks and keeping your workflow simple and able to debug and diagnose. As we saw with setting up our first task, Celery makes it very easy to instantiate new workers and to allow workers to auto-scale. We can also set up new queues with a simple configuration. Let's say we wanted to run two separate queues, one for just normal tasks and one for high priority queues. We can do so in our Celery configuration. So here I have the Celery app.py from our repository, and it has our configuration along with our application setup. All I need to do in terms of setting up a new queue is to import queue from Kombu, and then here in the Celery config, I can set a couple variables. First, I want to set my Celery default queue variable, and then I want to set my Celery queues. And here's going to take a tuple, and it's going to take as many queues as you'd like to pass here. So here I have default and priority. For you, you might need to set up different queues for different types of access. So you might want to have one queue that just handles database tasks, whereas another queue handles API tasks or anything that you may or may not want to wait upon. So I've actually already deployed this configuration on my server. And so we can take a look at the pipeline server and actually try running something in the priority queue. So here I am, and I'm in that same notebook. We can send a task specifically to a queue using the apply async method, which will take a queue name as an argument. You can also directly set this up in your task decorator argument if you always want that task to use a particular queue. So we're going to use this get stock info and use it with apply async this time instead. So you might see a slightly different syntax here. With apply async, it's going to take all of the arguments as a tuple. We could add keyword arguments as a dictionary next. And then we can pass extra parameters like queue after those arguments. There are many other parameters that you can use with apply async, so I recommend checking out the documentation to read more. We can check our results, and here we have it. It's important to keep in mind that Celery performs best when using granular tasks. This means you can and should try and break down larger long-running tasks into smaller, manageable, and maybe even embarrassingly parallel chunks. For example, if I wanted to compare two stocks with one another and decide which one is better to buy right now, I could do a get info lookup on both of them in parallel, and then I could use a comparison function with the final output. Celery allows several implementations to chain together subtasks in different groupings. The first we'll look at is chaining. Chain allows you to chain together asynchronous tasks and make them run synchronously. In order to use it, we're going to first import a few new tasks that I've created in the task.py folder, and we're also going to import it from Celery. Okay, so now I've defined my start and end dates, and I've imported all of the necessary tasks for us to do some of these synchronous and asynchronous operations with Celery. So I want to first create a chain. So if you take a look at my chain, we can see that it's going to run task price range, and then it's going to run task determined by. And as we can see here, it's using the pipe operator, which means it's going to output the price range task, and it's going to take that as the input as the next task determined by. And here, if you look at the task.py, it's just a really simple function. It's going to go and return a dictionary with a bunch of different information on that stock for today, as well as how the stock has performed from the start to the end date. And then the determine by is really simple. It's just going to say, is the stock price lower? Return true or false. And it's going to say buy if the price is lower than the average. Then we need to call the chain to get the results. You can see here that we have an asynchronous result. We can see it's already succeeded, and we can see that we should not buy Facebook stock today. The next more advanced task grouping is actually a group. This allows you to run many tasks in parallel and can be really easily used with a generator or an iterator. So I'm going to define a variable myStocks. So here I define my stocks as Facebook, Google, and IBM. Then I've created a generator inside this group object. And what it's doing is it's going to go call getStockInfo as a subtask, that's that .s, with the stock start and end. And as I can see, when I inspect my group, it's got a list of all of those different tasks. And what this can then do is run them each as tasks so that they don't have to run synchronously. They can run concurrently and speed up my process. Again, I need to call my result. I can see it is a group result, and I can call get, and I can see it's already done here. If it wasn't done, then this would just hang until it returned. Finally, there are chords, and they allow us to essentially group a chain and a group together. If you're familiar with directed acyclic graphs, this should sound similar. And if not, no worries. Just know that this means that you can perform a series of operations in a group and then combine all that with, say, an end summary function. There's one important note here that Celery chords will not work with every setup at the present time. They only work well with Redis and with a good persistent backend, like a database or AMQP as your backend. I have, for this example, set up my server to use Redis by changing the broker URL in my production configuration file. To create a chord, you need to create a header and a callback. You can do so in one line, but here we're going to do it separately so it's more clear. So here I have my header, and I decided to also use the subtask function. This allows me to pass the arguments in as a tuple, similar to the apply async. Before we were just using .s, which is shorthand for subtask. And so this generator is essentially my group object. Then we need to create a callback. The callback will wait for all of the tasks before running. So this can be very time consuming and it should be used with care. So my callback here is a sort results function. And what it's going to do is it's going to take all those price range results, which we know are dictionaries, and it's going to sort them by today's price from lowest to highest. You can look through the code at the task.py file. To call the chord, I merely need to place the header and the callback together. I'm going to time it so that I can see how long it takes. I'll use the time it decorator on my cell. For comparison, we can just try applying the sort results function without it being asynchronous to a grouping of the header. Let's try that now and see. Okay, so I can see that I'm calling the group function on the header here, and I'm going to need to call that function and then call get. And then I'm passing that into the sort results function. So for comparison, running it without chord, just as a group, and then performing the aggregate operation in Python, I can compare time. And we can see that this is much faster. There could be some caching going on within Celery, but it's unlikely. So when using Celery at scale, you want to keep data locality and network latency in mind. If you have 10 containers running with Celery workers and they don't have a shared data store, this could mean each task has to download all data associated with it, or that you might have millions of reads and writes happening to your database. The most performant case is to have the data in a distributed memory cache like Memcache. The least performant is to have each task downloading and uploading to other parts of your system. Even if they're fast like Amazon S3, this can add a lot of overhead. Think about what's needed for your application and try to design accordingly. You now have some exposure to a few different subtask operations, and you know how to run tasks on different queues, making scaling available to your machine. You can move forward by trying to determine if there's a better way to write some of these chord operations. Where would they perform best? Can you make a task where a chord is faster than performing it synchronously? That's my challenge to you, and I'll see you in the next video. Running a distributed system means you have more than one place to look when a problem arises. For this reason, setting up a good monitoring and alerting system is an essential part of being a good data pipeline engineer. Lucky for us, Celery developers, along with other open source contributors, have created a few great tools for monitoring your queue size, failed, and retried tasks, as well as what's running right now. We're going to take a look at one of them today called Flower. There's also a nifty command line tool called Curses. Setting up Flower is quite simple. It runs very similar to the Celery operation, and it has similar inputs and constraints. You'll first need to pip install Flower. I should already have it installed, but I'll do it anyways. And you can see I have a new Tornado version here. To start Flower, you just need to have your workers running, and then you can simply type Celery Flower. You're going to simply type a command similar to starting your workers. I don't have my Celery running locally, so we're going to take a look on my server. And here's the Flower for my server. I can see all of my online workers. I can also go to tasks, and I can see tasks performed here. And I can also use the monitor tool, which will show you a chart of all of the tasks. Now I'm going to go into my IPython notebook, and I have imported here the get stock info. To see Celery Flower perform, we're going to run a task. We can see that it succeeded. Let's go over to the Flower and refresh. And yes, I can see this. I can also click on the task for more information. And here I can see the arguments as well as the result. Now let's try and create a failed task. Let's try making up stock information. And we can see that it's failed. Let's go over to Flower, go back to our tasks, and we can see a failure here. If we click on it, we can actually get more information, such as a traceback. This is showing us that we have a remote data error, which is what the Pandas data reader is going to return if we have error retrieving remote data. If you're using RabbitMQ as your back end, you can also inspect your queues with the RabbitMQ management plugin. That's installed using the Ansible script for my server. but you can also easily install it following the RabbitMQ documentation. The management plugin allows you to see what's in the queue, delete and purge queues via the browser. You can log in once you've installed the plugin at the URL given in the documentation. And here you'll need to log in with a user other than the default user as good security measure. And we can see here that we have an overview of our different queues. We can take a look at an individual queue, and we can see that Celery creates quite a lot of separate queues for different parts of the application. And here we could also delete and purge the Celery queue if we needed to. For more debugging of your tasks, it's essential to also add logging for monitoring purposes. Although Flower gives us some great insight into errors and running tasks, good logging is imperative for debugging. Rather than add logging to everything, try to log some important things for your tasks that might give you insight later. For example, we could log the arguments we get and their types, if we're worried about people inputting improper arguments. If we notice this was the case, we might add in a line checking or some tests and attempts to transform those data types into what the function expects. To give an example, we can take a look at the tasks file. And here we can see that we can add a line, a debug line, where we have start and end types are, and we pass the type of the start and the type of the end. This would then get logged as long as our worker is using log level debug. We can then look through the logs and probably fix the error. If we wanted even more type granularity, we could take a look at using MyPy type annotations, but for now we'll keep this logging here and see what types folks are passing when they call this task. If you're already using Sentry or Datadog, there's also ways to wrap your application so that it throws the exceptions directly to Sentry or Datadog. Then you can look at all of your exceptions in one place. If you're running a distributed Celery infrastructure, I highly recommend doing so because it can point out if potentially deployments are not functioning properly or if users are inputting something differently every time they're using a task. It's also okay to add and remove logging as the project grows and changes. Sometimes you need to add a bit more logging because you don't have insight into why the error is happening. Other times you might be able to take out some logging because it's not necessary anymore. Think of your logging growing and changing with your entire code base, so that gets the love and attention your testing, deployment, and core code gets. And don't forget to add alerting. Using something like Sentry or Datadog is a great way to keep up with whether the number of exceptions are increasing or decreasing over time. Happy monitoring and logging. Now that you've approached scaling, subtasks, writing your own workers, and tasks, let's move on to some more advanced features of Celery. In this video, we'll cover when and how to retry tasks, as well as how to run Celery as a cron. Let's say the Yahoo Finance API goes down. What will happen to our tasks? Well, they might all fail, and we might not have a good way to recover what those arguments were or how to retry. To do so effectively, we'll need to set up a retry error. Here's how we do that. So here I'm in my text editor in my task.py file, and I'm going to go down to the price range task. This one is the one that directly calls the Yahoo Finance API via a GET request from the request library. First, we need to make our task self-referencing, so we can call the task retry method. To do so, we add this bind equals true to the decorator. We then need to update our variables. So when bind equals true, the first object that will be passed is the self task itself. So it's a self-referencing object. And so we know that we have self as our first argument. Then the rest of the arguments can follow. So we also want to make sure that we import the proper exceptions to catch. I know that Pandas uses URL lib for this method. So in the top, I've imported URL lib error, HTTP error, and URL error, which are the most common errors that you'll see if something goes down. We can now refer to our own task object, and you can see we've added a try except block here. So what it's going to do is it's going to try to read in the URL via the Pandas read CSV method. And if it encounters an HTTP error or a URL error, it's going to log an exception, and then it's going to raise this self.retry method. And you can see that I'm also passing the exception in to this retry method. This can help debug, and it can also help if you want to just bypass some exceptions, or if you want to have a max retries when it sees certain exceptions. Rather than retry everything, try and be cognizant of what tasks really need a retry and what ones are able to fail and be diagnosed later. Again, a retry is best if you know why the task failed and are retrying because you think it might succeed. Retrying just for the sake of retrying, if you don't understand the problem, will likely not change the outcome. Finally, if you're running only one worker, retry won't work because they will always go to a different worker on retry. So using retry on a small queue that might have auto-scaled to one worker is a bad idea. So outside of retries, I also wanted to talk about Celery as a cron. If you want to use Celery as a cron replacement, you can do so by writing a simple bash script to call a file and have that file call a task. But you can also do so more directly in Celery by using the Celery cron, or Celery beat as it's called. I'm going to take a look. So I'm going to open Celery app, and I'm going to scroll down. So when you use Celery beat, it uses this Celery beat schedule option in your configuration. And you can see here that I've created a new Celery beat task name, and that's get stock info 60 seconds. It has a task, a schedule, and arguments. And here's where you'd pass in the task name, you'd pass in the schedule, and you'd pass in arguments that you want to run on that cron. We can see here that I can pass a time delta object. This can also be several other objects, or it can be a particular date time. So you can look through the documentation for more information. Now to run this, I need to go back to my terminal. Since I'm going to be running it locally, the first thing I need to do is I need to make sure I start my workers. So I'm going to use the multi-start command, and this is going to start them in the background. You can see that I'm in my data pipelines virtual environment and I'm in my Celery app folder. So here I'm going to run multi-start. I'm calling it with the tasks file so it knows what tasks to register, log level debug, and then I have my log file. You might need to set this up if you're running locally. If you use the Ansible script and you're on your server, then it should have already set up this folder. But this folder will need to have write permissions from whatever user you're using. So you might need to tweak the permissions. So this is going to start my 4 workers, and those all started okay. So now I can start Celery beat, and I'm going to do so in a separate process. So I've started it here, and we can see that when it first starts, it sets a schedule. And if you had more tasks, this schedule would be longer, of course. So it's waking up in 60 seconds. This is again running every 60 seconds. And we can hopefully wait for it to register a task. Okay, we can see that it sent the task and that it will try again in 59 seconds. So I'm going to open a new tab and I'm going to just tail my worker logs. And I can see that it's already received 2 of the tasks. So I can see that it's working. This is not really a very useful cron. I'm calling with the same arguments every 60 seconds. But you can see that if you want to use something like daily reports or updates that you need to run as a schedule, that this would be useful. Note that if you need these tasks to complete by a specific time, it's a good idea to use a separate queue for them and to keep the queue relatively quiet. Otherwise, they might get scheduled at the time you're expecting them to actually run, and when they do run, it will be hours later. Finally, I highly recommend reading through the Celery documentation for even more Celery features. It's a complex project with a lot of options available, and we've only touched the surface here. I recommend reading through the whole documentation, pour yourself a big cup of coffee. I promise that you will learn something, and I look forward to seeing all of your projects using Celery. Dask is a distributed workflow for large datasets, allowing developers and data scientists to parallelize large datasets and pipelines, either locally or across distributed clusters. Dask is relatively new, released along with a paper by its creator, Matthew Rocklin, for SciPy 2015. Despite its young age, it has seen tremendous growth and a very strong response from the science data and distributed pipeline communities. Currently in pre 1.0 release, Dask boasts more than 60 contributors and has received attention at many scientific and data conferences. Dask can be used as a way to parallelize a large dataset, such as a NumPy array or a pandas data frame or a bag, which is similar to a Python set but allows for duplicates. These out-of-core memory solutions can then be used even on your laptop with optimizations for CPU and load. Similar to how Apache Spark optimizes for transformations, Dask does similar optimizations and creates graph workflows, like the one seen here, that map the data analysis into concurrent paths. Dask can be used with many different file types, such as HDFS, HDF5, as well as simple text files like CSV or JSON. It has some nice syntactic sugar for importing many files at once and can handle zip files as well as downloads from URLs or S3. This is the documentation on creating data frames from different sources. Dask Distributed can be used to create a task scheduler or executor for your Dask workflows across many machines. But you can also use Dask multiprocessing or threading even on one local or large cloud server. It has some great visualization tools for showing work performed and statistics on your cluster, even if you're just running it using local threads or processes. This is, for example, a workflow. All of the blue signifies that that part of the workflow or graph is done, whereas the red is being computed. You can see here that Dask helps manage the memory so that not too much is in memory at once. There's ways that you can also help optimize this, which we'll go over. We won't be able to cover everything that you can do with Dask, but I encourage you to read through the use cases in the documentation to see many examples of how Dask is helping data teams solve big data problems. As the Dask creators espouse themselves, Dask is somewhere between managing your own threads and processes using bare Python and the more complex libraries we'll cover like Luigi, Airflow, and Spark. For that reason, it doesn't solve every problem. It's fairly sparse in some areas. That said, if you have a large shared data store and data scientists or analysts who are familiar with NumPy and Pandas, you can likely save yourself some time and trouble and use Dask to perform analysis and basic workflows via a shared notebook server or some other shared file server. In this video, we're going to take a look at some of the simple data types available in Dask. We will be investigating Dask arrays and Dask data frames, which are built off of NumPy arrays and Pandas data frames. As usual, the first thing you'll need to do is install Dask using pip or conda. Dask also has a variety of dependencies, which you may encounter depending on what you intend to do using Dask. For example, if you plan on using Dask to interact with HDF5 files, or you'd like to convert your CSV files to HDF5 and use them with Dask or even Pandas, you'll need to install and build your operating system's HDF5 library. For my Mac system, I simply used Homebrew to install HDF5, but my Linux systems differed between Ubuntu and Debian, so you might need to look up the exact details for your distribution. Depending on your setup, read through the Dask documentation and install what makes sense for your work. You might want to use Castra, you might use S3, you might want to set up your own partitioning schema. Depending on all of these, you may need to install helper libraries. Just be aware that if you see any import errors, this is something you need to debug. I already have Dask installed on my server running Jupyter Hub via the requirements file, as well as some of the setup files in my Ansible script. To begin, I'm going to start a Dask array. I've imported my two main data types from Dask here, and I'm going to use the Dask array to create its own array of random numbers. So here I've created a relatively small array. It's going to be up to 100 with a 30% binomial distribution, and it's going to have 1,000 numbers. And here I've also passed chunks. So every time you create a new Dask array, you'll always need to specify chunks. Dask is going to parallelize your work using those chunks, so you should always choose chunk sizes that make sense for your data. You want to make sure that each chunk is small enough that it can easily fit into memory. Here my chunk size is 100. Again, this is trivially small, but it's good for an example. I can see the size using the size attribute. I can also use slices like a normal array. And here I can see that it's returning a simple Dask array pointer or transformation. If I actually want to see those values, I need to call compute. So what you can notice here is that Dask arrays, transformations, and graphs, as well as really any Dask object, is lazy. So we're going to need to call compute in order to start running the work. This allows us to build up maybe complex graphs over time and then call compute when we want Dask to parallelize and actually run the evaluation. We can also take a look at how Dask has chunked the data by, say, taking a slice and looking at the chunks. So here I can see if I use the first 300, that I'm only operating on the first 3 chunks. This should be obvious, but when you think about how you may or may not be transforming or moving or sharing your data across different partitions, you should start thinking and looking at these chunks and determine, particularly in a distributed setting, whether network latency or other issues or shuffling or sorting might affect your performance. We'll talk a little bit more about this when we talk about Spark later, but it's something to be aware of when you're building a distributed system that could potentially be lazy evaluated with these different partitions. We can also perform aggregate operations like max, min, mean, and visualize the resulting graph. And here we can see the graph of the different ways that Dask is going to parallelize our operation. And we can see here, because we're using Dask to create randomness, that some of this lower level is all the creation of the random numbers, and then it gets evaluated into the maximum function. And we can actually compute our max. Now that we've taken a look at arrays, let's move on to data frames. We're going to be using the vehicle theft database from Chicago Police Department that's available via the Analytics Edge MIT course. I've cleaned it up and I've added some fields using pandas. The notebook and the raw data are included if you want to follow along in your own time. To begin, we're going to use the familiar read CSV method from pandas. So normally what I do with pandas and what I also do with Dask is I first take a look at head, which will show me the first few rows, and then the D types. This will give me a good idea of what different objects we're using, what methods might be available or not available, and if I have a clean data set. So here I see I have date, date time, hour, day of week, and the lat and long variables for these motor vehicle thefts. And here I can see quite a majority are imported as floats, and then I have a few objects. I know from all of my work with NumPy data types as well as pandas data types that this means that they're stored as strings. That's usually not very useful, but here I know I can work around it because the way Dask is going to parse strings. I also know that these datetime strings are sorted. Dask partitions the data frames based on index, and it often works best if you set an index early that you know you can use. The best index is a sorted one. Because I know the datetime column is sorted, even if it's a string, I can use it to set the index and I can pass sorted equal to true. So now I can check out the divisions. And here I can see I have 2 divisions. It looks like the first one is going to hold a majority of the data because the second one starts on the 31st of 2012, and I can see here that's nearing the end. If I wanted, I could set my own partitions. We're going to use the set partitions method of the data frame, and then we can set our own partitions. I'm going to set up 1 partition per year. And first I need to import datetime, and now I can rerun this. It should be fine. Okay, so here I've created my dates, which should show a string with the first of every year, starting directly at midnight. I set them as strings because I know my index is a string, again, from the D types. Now I can use the set partition and set my dates. I'm going to create this in a new data frame 3. Then I can check my divisions. And again, so it's created a division for each of those dates. Everything in between those dates is going to be in that partition. To see how Dask operates differently, giving different partitions, we can visualize a few aggregate functions. Let's say we wanted to count how many motor vehicle thefts happen on each day of the week. We can do so with a group by and an aggregation. And let's compare our DF2, which as we know only has 2 partitions, as well as DF3, which has 1 for every year, or 12. So for our 2 division visualization, we can see that here it was able to do so actually only reading 1 block. And we see it's a pretty clear graph. Let's use our set partition, which we know has quite a few more partitions. And we can see that we have quite a bit more complexity in this graph, that it starts out looking very similar, and then due to our partitions, it parallelizes and grows more complex. Now you can see there are times that you may really want to split up the work like that, and you may have a good way of distributing it across many different workers or across many different nodes. But you might also want a simpler graph. Thinking about your data and your system and what summarizations you might need here is an important part of really unlocking the power of Dask and also making the call when it might just be faster or easier to run pandas on a larger machine. To actually compute my group by and get results for the counts of the days of the week, I can run compute on an aggregate group by. And here I can see that the day of the week, which we know in Python starts with Monday and ends with Sunday, that there seems to be a slightly higher activity around Friday. We singled out the hour series so that we wouldn't have just a chart here showing the same numbers, which is what count would have done for us otherwise. I can also use the value counts to sort from highest to lowest. Let's take a look at the different times of the day and see if there's a difference depending on the hour of the day. And I can see that these are floats. For me, that's a little bit hard to read. So I'm just going to chain together an as type here. Okay, this is a little bit easier for me to read. And here I can see that most thefts are occurring in the early evening up until midnight. But in the early hours of the morning, it's actually a much lower number. This is interesting. So in Chicago, it's better to stay out with your car parked in a nice, well-lit garage until about 1 a.m., and then you can go park wherever you feel like. So in this video, you've learned how to manipulate data and perform aggregate operations on both Dask arrays and data frames. I challenge you to use the time_it magic function and see how these methods compare to NumPy and Pandas. Did you see a speed up? If not, you can try expanding the dataset until you do. So again, Dask is going to work fastest and much better than NumPy and Pandas only when you get to where you need out of core memory. So depending on your local machine, you might need to create quite a big array or a big data frame to see a speed up. I've included an easy method from the Dask documentation for creating a much larger time series data frame. So use it at your risk, and I hope you can experiment with the performance improvements that Dask can give you. In this video, we will cover a new Dask data type, the Dask Bag. If you currently use Spark, Dask Bag will look very familiar to you as it has many methods and attributes similar to the Spark data frames and resilient distributed data sets. No worries if not. We'll see many of the features of a Dask Bag, including how to create bags, use filtering and aggregate operations, and parallelize execution of those aggregations. Dask bags are very useful when dealing with less structured data like JSON or text. For our example, we will use GitHub archive data and investigate natural language in GitHub messages. I was interested in the users active around the change of the year from 2015 to 2016. I imagine that they might not be enthused about working on New Year's Eve. In order to download the data, you'll need to run these commands. They actually don't expand well in Jupyter Notebook, so you'll have to run them in your terminal. This downloads all of the data for 12/31/2015 and January 1st, 2016. If you don't have wget installed, you need to either install it or you can directly download this data via your browser. Because I also want to investigate performance, I loaded Bokeh. Dask uses Bokeh for plotting. So now we have it loaded, and I'm using this output notebook so that it outputs the graphs to the notebook. I've based this notebook off some code from the Dask examples repository available on the Dask GitHub page. First, I want to read in text and create the bag. I can do so using the wild character syntax, which will expand and select files in the data folder with those file handles. Since the data is in JSON format, and I'd like to deal with dictionaries, I can use the map function to pass all of the data via the JSON loads command. To get an idea of how many records I have, I can use count. Similar to the other Dask data structures, I need to call compute since the method is lazily evaluated. Okay, so I can see that I'm just under 900,000. I'm going to take a moment and clear some of the output for us. To get a feel for what's in my data set, I can use the take command. This will sample the first n records in my data set, depending on the number I pass as an argument. So to take the first one, I can just take 1, and then I can access that via an index. Here I can see that this is a watch event. So I'd really like to focus on push events because this is people that are committing code during this time period rather than watching or starring or creating issues, etc. So I'm going to take a look. I know that the 10th one is a push event, so I'm going to take a look. And here I can see that there's a little bit more information. to focus on here is that commits is this nested list. So if I'm going to look at each commit, I'm going to need to kind of unnest that list and get access to all of the individual commits. We can also see that there's some other interesting fields here for us to take a look at. To investigate the frequencies of different events in my dataset, I can use the pluck method, which selects a particular key, and the frequencies method, which is essentially like the data frame's value counts. So this code will show me the frequencies of the type attribute in my data. And here I can see we have a lot of different events, but push events is a pretty large number, as well as create events. And after that, there's some that are just less frequent. I was curious as to what time of day the commits were coming in on New Year's Eve and New Year's Day. So I first want to separate out the hours element from the timestamp. I can use pluck with some regex to do so. So first I'm going to compile a time pattern, and this is going to use a named group to pull out the hour. Then I'm going to use filter. Dask bag filter can be passed any function which will return a Boolean. So here I'm making sure that the type is a push event. Then I can use pluck to pull out my created at, which is my timestamp, and I can use map to go through each of those created at timestamps and use research to pull out the group hour. So that's going to use that regex, find the hours, and pull those for each of the created at, and then it's going to put all of those into an hours bag. Then for this top 10 hours line, I can use frequencies along with top K, in which it will take the top n values of whatever bag I give it. So in this case, it's going to sort them by count, and then it's going to return the top 10 counts of the hours. And these are counts of different pushes during those hours. And finally, I need to call compute, and this will return the actual list of the top 10 hours that people were committing push events. So I know that these times are UTC, and it looks like they're mainly focused in the early afternoon, early evening time. Since I don't have geographic information, I can't determine what time zones the users were committing these in, although I am curious. To note, these are only tracking the push events, not all commits. In the Dask documentation, the authors encourage you to utilize fold by whenever possible, as it is faster and more parallelizable than group by operations. So if you need to do some grouping, try to see if you can operate it with fold by. Fold by is very similar to many MapReduce operations. First, you need to create a function that is a grouping. Here it is our getHours function. Then you need to create a mapping function. Here's my binary op function, and this is going to continue to add to a total a length of the number of commits. So this is going to be a number counting the number of commits in each push event. Finally, you need the reduce operation, which is this combine, and that's going to essentially combine each of the keys together so that I have a total at the end. So to call the fold by, you simply need to have your bag called fold by. I'm going to pass in your grouped operation, your binary operator, and then a combine operation along with an initial value. And here I'm just pulling the top 10 using that top K. So let's take a look. Okay, and here I can see some similar numbers and timestamps. We don't see a very large difference in performance time in these. However, fold by is faster when you get to a much larger data set. I was also curious about doing some simple bag of words natural language processing with the commit messages. First, we need to do some pre-processing. We're going to pull all the messages, and we're going to create one long string that is going to hold all of the messages of each of the commits. This will be like a long string of each commit message from each push event together. Then we can use Dask Bags string operations to identify the most frequent words. So first I'm going to pluck payload, which is going to have messages within it. Then I'm going to go grab the message from each of the commits, and I'm joining them together with a long string. Then I can access the string operator of this bag because I know that it has strings in it. And I can use split and concat. This is essentially just going to create a list of each token. Then I can use frequencies and top K to pull the top 10 words. So here I have my words, and other than a few like update and merge, these are very common words. So a standard thing to do in natural language processing is to remove the stop words. I'm going to use NLTK to do so. NLTK is a very popular Python natural language processing tool. So if you need to install NLTK, you need to do so now. And if you haven't yet downloaded any of the words, then you'll need to follow these instructions to download the stop words. So I've already done this. So now I can import the stop words. I want to create a simple function that's going to create, again, that really long string of all the different commit messages. And then it's going to remove the stop words. So here I'm just doing exactly that. And I'm returning a long string, and now it should be void of stop words. So here I can just see a few of them. If I want to look at all 5, I can do so. And I can see that I don't see any stop words. Then I can use those same split concat frequencies and top K iteration to take the top 20 most common words without the stop words. I want to visualize this, so I'm going to use the profiler. You can use this for any compute operation or any of the times that you're calling results, you can use this profiler. So now my results have come back, and I can see that I have one worker running. So this is some of the reason why my tasks are taking longer, but I can also use this profiler to look at how long each of the different methods took. Yours might look differently if your Dask is operating outside of one worker. Finally, to see my results, I can call my result. And I can see here I have update, add, merge, fix. I have much more different words than just simply end of the. So this is much better results. So I challenge you to take a look of at least one new feature in this Dask Bag dataset. Can you investigate the most prolific committers during this time, or the most committed to projects at this time? For hints, you can take a look at the Dask examples repository, which has some code for loading commits by author to get you started. Don't forget to use the profiler to see how your code is performing. In this video, we'll be covering how to use Dask in a distributed manner and how to easily parallelize simple Python work in Dask using Dask Distributed. With Dask Distributed, you can use distributed computing alongside Dask data models for even faster data processing. If you're interested in using Dask for simply parallelizing already written Python code without using Dask models, you can take a look at this Dask delayed documentation. With a simple decorator on your functions or calling delayed and passing the different arguments, you can use Dask to then parallelize your work. Note that not all features are supported in these type of functions. Namely, at this point in time, you cannot use your results as iterators or utilize results for logic pathways. However, if your code simply takes a dataset, applies some math or algorithms to the data, and stores the data, for example, pre-processing data, then using Dask Delayed is a good option. To learn more, I recommend checking out the documentation or watching some videos on YouTube from recent conferences. We'll be moving to use Dask Distributed, however. To use Dask in a distributed manner, you'll need access to more machines or spin up some virtual machines on your cloud computer. There are some shortcut scripts for deploying with an Amazon cluster as well as tearing it down in the Dask documentation. Similar to Celery and other distributed task managers, Dask Distributed uses a scheduler which keeps track of the multiple workers and tasks. Unlike Celery, if one client working on some computations closes the client, Dask will remove those tasks. As with any other distributed work, you need to think about distributed problems, like latency, which is how long it takes to send or sort data from your network or disks. Data locality is all of the data located on the same node. If not, how many nodes or workers will your task have access to compute the result? And stragglers, when tasks which rely on all previous work to be finished are held up by one slow node or one final task, this can delay the entire computation. Using opportunistic and intermediate caching will help with some of these problems, allowing your data to be stored locally and easing network load. Dask has a few ways to do this in a larger scale, outlined again in the documentation. For complex setups, the authors recommend using Dask Distributed rather than Python multiprocessing as your scheduler backend, as it's been optimized for that use. The distributed scheduler uses a last-in, first-out schema, attempting to clear up linear workflows. For example, if your task just finished a sum and now wants the average, that's going to do that in order and free up memory for later tasks. So to show the use case for Dask Distributed, we're going to compare running some API requests and performing some data extraction in sequence. Then we're going to compare using the Dask Distributed scheduler and see whether in sequence or the distributed scheduler works faster. So here I'm using the Dask Distributed notebook from the repository, and I'm going to import in libraries we're going to use. To run it locally, you're going to need to set up a config with an Open Weather Map API key. So you're going to need to go there and get an API key. And the idea of the script is that it's going to request from this Open Weather API twice. Once it's going to get the current weather, which is this method here, this function here. And then it's going to get the extended forecast, and that's this function here. Then it's going to filter the temperature. So these forecasts give quite a lot of data back, and we're just going to filter and pull out the temperatures and the humidity. And then it's going to merge the results of those filters together so that we have one per location. Finally, I have a main function here, and that's going to essentially call all of those methods in order and allow us to merge them all together and return that finalized dictionary for each place. We have a get config method for pulling in the config. It's going to request that that config be either in the current directory or the parent directory. And then I have a list of cities. This is not that long of a list, but it's good enough to start showing the comparisons. I challenge you to, as homework, find a really long list of cities or aggregate one yourself and see if you can show an even greater difference in Dask distributed use versus just parallel use, or you could even implement it with Python multiprocessing and compare Dask to multiprocessing. So you don't have time to go over every line of code, but again, this is in the repository. To do the comparison, we're going to simply create this results list. We're going to append each of the results from calling it individually. And we need to have an exception here because there are some errors with some bad city names. Then I'm going to sort by current temperature and sort by upcoming forecast temperature, putting the warmest at the top. So when I run this, it's going to run them again synchronously. And I can see if I scroll down that I have my data, my sorted lists. If I scroll to the very bottom, I should be able to see. This took about 9 seconds. So I have some instructions here on how to run Dask Scheduler. So if you're not worried about looking at the diagnostics, then you can use the local cluster. And the code would be like here. For my computer, this did not work. I'm not exactly sure why, but it could just be that the host naming and the way that it's binding to different addresses doesn't really work with a more complex setup, or if you have a lot of other services running. It also didn't work on my server. However, I do use Screen on my server. Screen is a great tool, and you can basically use it to have terminals open even if you're not logged in to your server. And so I have some instructions here on how to run Dask Scheduler, and then you need to start the Dask workers. And this should work either locally or on your server if you want to do so. There's also a bunch of different ways you can use SSH to run your cluster. Again, they have some recommendations for EC2. So take a look through the documentation for Dask Distributed if you want to look at different ways to run it. So if you're running it similar to me, then you can call this executor function. In the latest release of Dask, the executor is renamed to client, but so far these terms are exchangeable. It may come to pass, however, that Dask gets rid of executor in favor of client, so make sure to check the latest documentation. I'm also going to open up my diagnostics server. So now I have my diagnostics server, and I can see that it's going to track my memory usage, my CPU, network, as well as show a task stream here and task progress. So we'll keep an eye on this as we execute our code. So first what I'm going to do is you can see I'm using the executor submit, and that's going to submit to the main function each of these I that I'm iterating through, which is each city in the city list. Then I can see my futures, which should be a bunch of pointers to those future tasks that will finish. And finally, then I can call result for each of them when they finish. And here I'm going to make sure that the status is not equal to error. So that is going to avoid calling the exceptions that are raised and do the same comparison. So let's take a look and run this. And while we're running it, we can take a look over here and we can see all of the different tasks that are completing. So here are my main functions. You can see I'm running it across 8 workers. Here I can see my network. And if I go back, I see that it has completed. And if I scroll down to see the time, we see 1.71 seconds. So this is much faster than doing it in a sequential manner. I want to also show that you can access errors in a special way. So I know that the final future threw an error, so I can pull it using an example error. I can check the status, which is again is error. And if I call result, then I should see the value error that my code raises. And again, this is some bad data because somewhere WL doesn't exist. So I encourage you to add a few functions to this. One suggestion is maybe calculating the lowest and highest temperatures, or to calculate the range of upcoming forecasts and sort them by range or by lowest or by highest. To see more from your profiler view or this distributed diagnostics window, you might want to add in a few other functions. So instead of just calling main, see if you can call a few different ones in a row. You might also want to add some random weights into the code. This should give you an idea of how random weights like sleeping and other things like that, or waiting for a return from a slower API, will affect your parallelization. There are many more things that you can do with Dask, including fairly recent development for machine learning called Dask Learn. So if you're doing machine learning, especially if you need to do a search for the different parameters that you're going to input and you want to do a simple CV search, then you can do so with Dask Learn. I encourage you to keep learning and to use Dask for more of your data analysis projects. In this video, we will review what directed acyclic graphs are and why you should be using them for your distributed data pipelines. The good news is, if you're already using data pipelines, you're already likely using directed acyclic graphs, otherwise known as DAGs. DAGs are simply graphs which are finite, directed, and acyclic, meaning if you start at any vertex and follow the path via the edges, you cannot end up back at the same vertex where you started. DAGs can be simple or complex. This simple DAG, courtesy of Wikimedia Commons, has 7 vertices, shown labeled A through G, and 8 edges, shown as the arrows. With DAGs, your edges are always shown going from one vertex to another, meaning they're directed and acyclic. DAGs can also become quite complex. Here shown is a more complex DAG from Oxford University's Journal of Bioinformatics. This paper is on gene ontology. As we can see, there are still directed edges and a finite number of vertices. So what do DAGs have to do with data pipelines? As you begin using libraries like Dask, Luigi, and Airflow, you'll notice visualizations of your data pipeline workflows. Take a moment and think of a workflow you have built or used. They begin at some point, let's say data ingestion, and go through a series of steps before the pipeline ends, likely in data storage. These workflows can be represented as DAGs because they are finite in steps, they have a beginning and an end, and they move via a series of steps and therefore are directed. Graph theory and analysis has been a part of mathematical study since the mid-1700s, and quite a few breakthroughs have occurred since then in terms of the theory, research, and understanding of graphs. You may be familiar with Leonhard Euler, the famous Swiss mathematician. He wrote a first paper on graph theory analyzing the 7 bridges of Königsberg. His aim was to create a formula to determine edges and vertices for movement throughout the city. Here's a map from MacTutor History of Mathematics that shows the edges highlighted in red. Graph analytics has developed to include real-time large-scale graph analysis, for example, using map routes to determine the best or fastest way from one place to another, or analyzing how proteins or genes interact with one another. As we learn more complex workflows via Luigi and Airflow, graph analysis in these frameworks will help determine best paths for our task completion and prioritization. Now that we have a better understanding of DAGs and graphs, let's move on to writing some Luigi and Airflow workflows. In this video, we will cover some general comparisons of Airflow and Luigi, two of the major Python data pipelining frameworks available for designing workflows via code. This is by no means meant to be an exhaustive comparison, more of a general overview of the present state of the projects. As we all know, software grows and changes, so you should take time to read through the documentation of each of these projects and determine which best fits the needs of your project or team. That said, let's review a quick history of each of these projects. Luigi was developed first by Erik Bernhardsson and Elias Freida at Spotify in Sweden. Luigi's origin began via a smaller project called Builder 2. After struggling with Builder 2 issues, Erik and Elias decided that they wanted a more extensible solution, something like new make for workflows. They began development in late 2011 and open-sourced the project in late 2012. The first major shop to use Luigi outside of Spotify was Foursquare. Luigi is currently used at numerous large and small-scale technology companies, including iHeartRadio, Bitly, Asana, and Stripe. Airflow was first developed by the Airbnb data team. It was open-sourced in June 2015 and became an Apache incubator project in March 2016. Airflow is designed to easily abstract and manage data pipelines and the extract, transform, load, or ETL process. It currently has less large companies using it due to its younger age. That said, Airflow is used at Zendesk, Blue Yonder, Glassdoor, Handy, Lyft, and Postmates. Let's begin by covering some of the similarities between these projects. They're both open-source projects built purely in Python for easing management and abstraction of ETL and data pipelines. They both integrate with a variety of data sources, including Hadoop, S3, a variety of databases, as well as other file systems. They both have the ability to use a database to store task history and keep track of what has run and whether it failed or succeeded. They both allow task and DAG execution via subprocesses and managed workers. Finally, they both have the ability to easily list dependencies and task execution order. Now let's move on to some of the larger distinctions between the two projects. One large difference is scheduler support. Currently, Airflow has built-in scheduling support via the executor, whereas Luigi advises users to rely on cron to start task processes. Another difference is the ability to scale. Currently, Luigi is used in an enterprise level with tens of thousands of DAGs managed, whereas Airflow is working out several issues regarding stability and running of a large series of DAGs for an extended period of time. These issues will likely be fixed during the incubation stage in a future release. Another stark difference is the web interfaces. Airflow has a very nice and detailed UI, which gives you insight into the processes, DAGs, as well as the current status of all running, failed, and completed tasks. Luigi has recently built a status view of each DAG, but the UI has less features than Airflow, and the graphs can sometimes be difficult to follow. Task definitions and status are handled differently in the two frameworks. Luigi defines tasks by a combination of task names and past parameters. It tests whether a DAG is done by monitoring the inputs and outputs. A failed task within a DAG is restarted as long as there are workers present to note that the previous task was performed, but the failed task output is not yet complete. Airflow instead uses a user-defined DAG ID and then a series of scheduling and parameter rules to define their tasks. The user can set up retry rules, but the input and output are not tested as part of the process. Some other differences include the fact that Airflow ships task code to its workers, whereas Luigi workers are set up by running a particular Python file where the tasks are defined. Therefore, the Airflow workers are centralized, and the Luigi workers only know how to perform whichever task they were started with. To perform centralized scheduling, Luigi uses Tornado, but this central scheduler will not start up new workers. In contrast, Airflow uses Celery to start up new workers as the queue grows. Both frameworks have ways of dynamically generating tasks and managing lost data. For Luigi, tasks can yield other tasks in their main run method to generate state-based tasks. For Airflow, tasks can be dynamically generated directly in the DAG definitions or Jinja templates. If data is lost in Luigi, as long as the proper workers are running, it will start the backfill via tests of input and output state. If data is lost in Airflow, you can delete the tasks from the state database, which is usually MySQL or Postgres, and then set them to run again. The Airflow state database, therefore, is a point of failure for systems and should be treated accordingly. If you have a particular need to interact with a certain kind of data, say Spark, BigQuery, Redshift, S3, you should consult the documentation and ensure there are proper hooks. Luigi has quite a few at present, but Airflow support is growing. If you need to define complex workflow triggers, they each have their own approach. So make sure you write some pseudocode for each framework and ensure whichever one you use can support your workflow out of the box or with little alteration. In this series, we'll cover both workflow frameworks, so don't fret if this was a whirlwind introduction. You'll soon be writing DAGs for each and can likely better determine if either of them fit your present data pipelining needs. In this video, we will be taking some initial steps to get Luigi installed and run our first task with Luigi. If you've already installed the requirements file or installed the Conda setup, you should have Luigi installed. You can test it by running Luigi on the command line. We can see that we don't have any tasks specified, so Luigi sends us a message. If you don't see this message, please install Luigi via pip or Conda. Luigi requires that we specify tasks in Python scripts. I've built a few examples in our Luigi folder. Let's take a look at the file taxi data import. So I'm going to open this up in Atom. So in this file, we have a series of tasks, and we can see each task is a subclass of the main Luigi task. We can see that here. Let's focus on the first task to see the different elements of a Luigi task. So if I scroll down so that we can see a little bit more of this first task called download taxi URLs, we can see first that it has a list of parameters. So all of these parameters are different attributes that we're setting for the class, and we're defining them using the Luigi parameter classes. So here I have a simple parameter in the URL list in the cab type. I also have an int parameter, which is going to only accept integers, and I have a list parameter, which is going to only accept lists. For each of these parameters, I have a default set. If I didn't want to use defaults, I could always make sure that I'm setting my parameters when I call the task in command line, or I could pass parameters from the task beforehand. We'll see an example of this later. The main action code of each task occurs in the run method. So if we look through this run method, we are first making a request to our URL list. This is our parameter set up before. Then we're going to make a list of possible strings, which takes a few of our parameters. And then we're going to iterate over different lines, and we're going to match these possible strings with our cab type and our lines. So if we take a look at this raw file in our browser, we can see that it contains a list of different CSVs. These are all data CSVs of New York City taxi data. And we can see here that at the very end of each, we're going to have a year and a month combination. We can also see by scrolling down that it has green taxi data as well as yellow taxi data. So going back to our file, if we take a look, we're going to try to match just the year and the months that we have set in our parameters, as well as the cab type. So here we're just getting yellow cab data from June, July, and August of 2016. We can see that later in our run method, we call the self output, which is another method Luigi tasks use to return an output target. These targets can be files, which is what we have here, or they can use clients to connect to things like S3, databases, Hadoop file storage, and a bunch of different options depending on what you need for your task. There's additional mock files that you can use to essentially pipe the output to the next task. So if we look here with our output definition, we're writing to a local target, which means a local file, and it's going to be in our temp directory in a folder called taxi data, and it's called URLs. So if we want to take a look just at the next task down, we're going to notice a few different things that were not in our last task. The first things that we notice is that the first method is actually requires. So using requires and output is essentially how Luigi knows what to call and how to determine what has already been called. When Luigi sees a task it needs to perform, it will ensure all tasks defined in the requires are finished. Luigi determines a task is finished by testing the output of that task. For our requires, we see that we list only one task here, but we could list as many tasks as we wanted to if we needed more than one task to complete before we could run. We can also see that we have an input parameter, which is where we define another target. By defining our input and output, we can use them as methods and then call the particular file operations on them via the target object. If you want to see all methods available to your chosen target, take a look through the documentation. One really nice thing with using built-in input and output methods is Luigi will take care of opening and closing them, as well as making sure that we have a lock on the file while we are using it. This is to say that Luigi helps us build around possible race conditions with our tasks and handles these atomic operations well. We will spend some time going over the rest of the file in a later video, but I encourage you to read through it and see if you can make out what's happening every step of the way. To actually run Luigi, we need to call this task using the Luigi command. So I'm going to go back to my terminal. So let me use clear. Okay, so here I am adding the local directory. I'm in the Luigi directory in the repository, and I'm adding the local directory to the Python path. This is because the way Luigi is going to discover the module and the task is by looking in the Python path. At a later date, you probably want to either set this up directly in your virtual environment or set this up in Luigi configuration, but for now, this should be a fine way to run it. You can then see I'm calling the Luigi command. I'm passing the module, which is taxi data import, that's the name of the file, and I'm calling the task name. And then I'm going to call the local scheduler. So when I run this, I can see that it ran successfully. Luigi tells me that this project looks smiley face, and you will get used to seeing these smiley faces or frowning faces depending on whether your tasks succeed or fail, because there were no failed tasks. So we can see that one task ran successfully. It again gives us all the parameters. Before starting the next video, try running the download taxi data task the same way that we ran this task. Note, it will take a while because the files are large. If you want to play around with downloading different data, you can also set the parameters directly in your command. So if we were to use this command and we wanted to say download green taxi data, we can literally set cab type and green. And here I have it incorrectly. I was using what I call the parameter, but you'll see that Luigi replaces the underscores with hyphens. So I will need to use cab type equal to green. And we can see here that despite me changing the parameters, Luigi didn't rerun the task. Can you guess possibly why this is? So as discussed, Luigi is going to check the output. To rerun this task, we're going to have to remove the output. So I'll leave that to you, and congratulations on running your first Luigi task. In this video, we'll review some of the other tasks and methods you can write in Luigi, specifically focusing on more complex tasks that do dynamic things, as well as tasks that don't directly inherit from the Luigi task class. We are again taking a look at New York City taxi data. Hopefully you've been able to run and download the taxi data by running the download taxi data task. If not, you can still follow along, but your tasks might take longer to complete. In taking a deeper dive into our download taxi data task, which is here in our taxi data import file, we can see that we're using the yield command in the run method. So that is here down on line 51. Python's yield is often used by generators to allow for memory-efficient iteration. What we use yield for here in a Luigi task run method is to dynamically generate new tasks in the workflow. This allows our download taxi data task to get the file names and pass them dynamically to download file, which then can actually do the work and produce the necessary output files. So if we look down here at the download taxi file, we can see that when this runs, it is actually copying the file from the response to the local output. So this is one example of how you can dynamically, from your inputs or from whatever it is that your task pipeline finds, you can dynamically generate new tasks. And this is really useful. So moving down in the file, you can also take a look at how to define a different type of task. So these are all here Luigi tasks, which have similar attributes and methods. But when we come down to class save taxi row, we can see that it's inheriting from SQLA copy to table class. So this is a class defined in the SQL Alchemy module, which is what SQLA stands for. And what that's going to do is it's going to have a way that we can use our data and connect to a SQL consumer. Here we're going to connect to SQLite. So we can see that we have different attributes. So for example, instead of setting parameters, I'm setting things like connection string, table, I have a list of columns, and I have a requires. So if you take a look at the documentation for the SQLA module, you'll see that the SQL Alchemy handler has these different distinct methods and attributes which you need to use, which are different than using your local storage handlers. In the SQLA module, there are even more parameters to choose for things like should we add to our table or completely rewrite it. We can also define our schema, which is what we have here. And there are a few different methods to use to insert and update. So specifically with this SQLA copy to table task, we are essentially piping the requires directly into our database. And the requires is this task directly above it, which is called add taxi location. So essentially the output of add taxi location is being directly piped into our SQL Alchemy table. And if we take a look at how this is returning, we can see that it's using a mock file type. So here the output is this mocked file. The mock file is called add taxi location, which means it will be called by the requires from the save taxi row task. And if we take a look in the run command, we can see that it's doing several things. It's going to be adding some data from the Google Places API. This is to find Latin longs of pickup and drop off locations. And then what it's going to do is it's going to use this output open. So we can see that it's writing each of these records directly to the output. So it's essentially piping them into this mock file, which is then going to pipe them into the database. And we can see that the line is using tabs. This is how SQL Alchemy is going to determine different fields. You can change this, and this is again something configurable, but that's the default that SQL Alchemy is going to use. So now that we've investigated 2 new tasks, the rest should be pretty easy to read. To see them run, we can do so using the centralized scheduler, which would be what we would use in production or on our server. To do so, we first need to start the scheduler. I'm going to go to my terminal and I need to change into my virtual environment. Then I can use the Luigi D command, which is short for Luigi daemon. So here I'm going to be setting the PID file, which is the process ID file, and I'm just going to set it to something in this directory. You might want to set it up to be in a directory that, again, your user has the ability to write to. And I have my log dir here. So this is actually likely to throw an error because I haven't created that log dir yet, but let's give it a try. And of course, yes, it is. So I'm going to make those directories now. And I like using a specified log directory and a normal place to find it because for me, that just makes it easier. If I'm not going to be using systemd or something else to run it and keep track of the logs, I like to have my logs in my log directory if possible. So I'm likely using not familiar Mac terminology. My primary operating system is Linux, so please excuse my issues with giving a proper chown command to Mac. All right, so now that I have those things set up, I should be able to run this process. And because it's a background process, it's going to do exactly what you just saw on my screen. It's going to start running, and then it's going to fork into the background. So if you navigate to your localhost 8082, that is where Luigi runs. And now we can see the Luigi visualization. So in order to see this in action, we really need to run a task. But you can see that we have a few different panels here. We can look at our resources, and it gives us a few different views. So we can go back and I need to actually run one of the commands. So I can use clear, and then what I'll want to do is I'll want to actually call the task. So I'm going to use the add taxi locations task, which should back propagate and also yield the output to the add taxi location. You can choose the save taxi row here if you'd rather see that, but I would run them separately to possibly diagnose if you need something like SQLite or SQL Alchemy, then you can go through that. You will again also need a Google Places API key, which you can directly get from Google's developer API. As you can see in the top of the taxi locations file, there is a config directory expected to be called prod.cfg and be located in the parent directory within a subdirectory called config. So if you want to use a different file path, you can change the global variable and point it to your config file, or you can take a look at the example configuration file provided in the repository for the naming conventions. All right, so to run our actual task, we can use Python path, and we don't need to set that local scheduler. So we can just set the number of workers. Actually, you don't need a equals here. You can just set them to 4. I would recommend sticking with the amount of cores that you have. So 4 is probably safe. And then we can just run this. When we run this, we can start to see the different output. And if we go back to our scheduler and we refresh, we should see. So we have some done tasks. Here I have had a failed task. You can look at the dependency graph of any task, which you can do by taking a look here. And you can, of course, see the different variables. So Luigi gives many more options, some of which I've set up in the luigi.cfg file, which is the configuration file. There are even more settings that you can look at in the documentation, but you have what you need to get started writing your Luigi pipelines, whether they touch databases, files, or APIs. If you want to start with this simple pipeline and add on to it, there are a few things that come to mind. You could add the trip duration or the total trip time, or you can add borough names to each of the data rows. If you do, feel free to send a pull request. I also challenge you to write your own pipeline with Luigi and publish the code on GitHub. Whether it's converting a pipeline you have been struggling with at work into Luigi, or coming up with a fun solution to something that you would enjoy analyzing, simply getting the pipeline up and running in Luigi will help you think about dependencies, constraints, and it might help automate some pain points away. So have fun pipelining, and I'll see you in the next video. Because of its widespread use in enterprises and ETL or extract transform load pipelines, it's worthwhile covering Apache Hadoop and its many variations in a course on data pipelines. In this video, we'll talk about Hadoop architecture, the wide breadth of services available from Apache and other Hadoop ecosystem supporters, and learn how to use Hadoop file storage on our computers. What is Hadoop? When people mention Hadoop, they're usually referring to the Hadoop ecosystem, with many different services and tools built on the initial Hadoop project, which supports distributed file storage and distributed computing via MapReduce. Hadoop was first born out of the need for an open source search engine. In 2002, Doug Cutting and Mike Caffarella started Nutch to help their efforts at the Internet Archive project. This initial naive web crawler implementation began to grow into distributed architecture after a few important Google research papers came out covering distributed file stores and MapReduce functionality. Cutting joined Yahoo, and Hadoop was officially born and open-sourced, at which point several Google engineers joined the project, and it eventually grew to become the standard open-source enterprise software for large-scale distributed file stores and MapReduce that we know today. The Hadoop project is a fault-tolerant distributed file store with a built-in resource manager called Yarn, which stands for Yet Another Resource Negotiator. Data on Hadoop file storage is stored in triplicate across data nodes, and distribution of this data and which nodes have what data is tracked by the name node. A secondary name node can be set up to combat single point of failures. Hadoop is written in Java and can store hundreds of petabytes of data across tens of thousands of nodes and even more CPUs. It is truly big data. Hadoop is great for batch processing, and won favor with being one of the first open source big data MapReduce systems, allowing engineers to write simple code and process massive datasets in batch format. The system allowed scheduling of said jobs via templates in the Yarn system. With a shared nothing architecture, it allows for resilient job scheduling and data management. So here we can see one example of our triplicate data stored across our data nodes. We can see that the name node is going to track and send the data to our data nodes, and that a secondary name node is there in case the name node fails. They should have, of course, the same data. As we can see here, it could be that some of your data nodes don't even have any files on them. But if you have a larger distributed stack, this could be, of course, tens of thousands of data nodes. And then it is likely for particularly, let's say, your larger files to be first chunked, and then each of those chunks stored in triplicate across 3 different data nodes. If one of those data nodes goes down, then the name node will know to replicate that onto a new data node. So this is how it can have a high level of resiliency. The Hadoop project itself has spawned quite a lot of other projects that utilize or aid the initial design, allowing for SQL querying of HDFS, which is the distributed file store, streaming data with pre-processing, machine learning, workflows, pipelines, data analysis via statistics, scripting, and even more. We don't have time to cover everything Hadoop and its ecosystem can do, but it is a massive list, and depending on your pipeline's needs, there are likely Hadoop projects to address them. Many of the Hadoop projects live in Java, but there are quite a few with Python bindings or clients. If you are a Java or Scala shop, then this might make the appeal of Hadoop even better. To install Hadoop, I recommend looking for specific instructions for your operating system. I'm running Hadoop 2.7.2 on both my Mac and Linux, and it takes a bit of tweaking to get it running properly. However, following a good how-to via web search is a great first step. The Apache Hadoop site, pictured here, also has detailed setup for both single nodes for local testing and distributed clusters for production. In order to follow along with the next steps and with the Luigi with Hadoop video, you're going to need to install Hadoop, get your Java home and Hadoop home and any other environment variables that you might need properly configured. You will need to set up your core site XML and a few other XML configurations depending on what version of Hadoop you install. Then you will need to format your name node and start your name node and data node, which you'll most likely use the startdfssh command. Again, I highly recommend finding an article for your operating system and your chosen version of Hadoop and following along if this is your first Hadoop installation. Once you are running Hadoop, you can easily manage your files using this initial install and the Hadoop command line syntax. If you need time to get Hadoop up and running, I would stop this video and restart it here when you are properly running Hadoop. I have already installed Hadoop, so I'm going to exit OpenOffice and go to my terminal. So I can tell that I have Hadoop properly installed and running because I can see my HDFS command line completion. So if I type HDFS, I can see all of the different commands available to me. I can also use the help command, which will again print out all of the different possibilities. So what I'm going to do is I'm going to first set up a user directory where all of my files that I'm going to be using are going to be stored. And then I'm going to make a subdirectory. So we can use the make dir command. You'll find when you're using HDFS, a lot of the DFS commands or the distributed file store commands are going to be similar to bash commands you know. I can run HDFS and then I'm going to select DFS and then I'm going to make my directory. I'm going to call it user Hadoop. And here I've actually already created it on this Hadoop system. And so it's going to tell me that my file exists. For you, if this is your first time running it, then it probably should have just created it. And then I'm going to make a subfolder called data pipelines. So now that I have a folder to use, I can put my file there. So I'm going to take the MVT CSV in the data folder, and I'm going to put it into this new Hadoop data pipelines folder. I can do that using the put command. So it is in my data folder. I'm in the Luigi folder right now, so I need to go back a folder. And I'm going to put that one into my user Hadoop data pipelines. Now I can check and see using an ls command. And here I can see that motor vehicle theft.csv is there. And I can see some permissions and the size, all of the normal things that we would see with ls. I can also use some simple bash commands. Depending on your installation, you may or may not have all of the commands. So it looks like my Mac version does not have less, but it should likely have tail. And yes, I can see the last row here. If I wanted to grab a file from Hadoop and store it locally, I can use the get command. So I'm going to clear. I'm going to store it in my data directory. I'm going to give it a different name. That's going to pull it down. So I can compare them. I haven't done anything to either of them, so they should be the same. So I can compare my data movement CSV or motor vehicle theft with my data motor vehicle theft from Hadoop. And I see no difference. So these are just a few of the commands available, and we definitely haven't covered all of the features in HDFS or Yarn and MapReduce. If you're interested in learning more, O'Reilly has some great materials for learning Hadoop, along with a video course and several books. And there are a lot of great tutorials on the web. We'll be using some Hadoop features and data store as we continue learning data pipelines with Python. In this video, we'll be covering how to get Airflow set up on your system and test run some example DAGs or directed acyclic graphs. If you have installed the requirements for this video, then you already have Airflow. To get fully set up with Airflow, though, it's going to require a few things. If you wish to configure your Airflow home directory, it should be set as an environment variable, Airflow home. I can show you here. So I see that I have my Airflow home, and it's pointing to this folder that I'm in, Airflow. If you want to use the DAGs I've written for this course, you'll need to either copy these DAGs into the default Airflow home, which is the folder called Airflow in your home directory, or you can set the Airflow home environment variable in your bash profile or your bash RC. For Windows users, you can set your environment variables in your system settings or using PowerShell commands, or you can use the simple set command. So I'm in my Airflow folder, and I can see here that I have my Airflow config. Airflow will also set up a unit test config, and then I also have my DAGs folder. And in my DAGs folder, we can see the two DAGs we'll be using, as well as a Subdags folder. So the first thing that you'll need to do with Airflow is run initdb. So I'm going to do that right now. And initdb uses Alembic to initialize your task database and migrate it so that it matches the latest Airflow release. As you may recall from our initial review of Airflow, Airflow uses this database as a truth table for what is complete and incomplete in your task list. So we can see here now that we have airflow.db. If you don't have MySQL installed, you'll also likely need to install it and change some of the configuration in the Airflow CFG file. Airflow uses MySQL for the Celery database, and if you're using Python 3, you'll need to install MySQL Client Python, which is a special Python 3 version of MySQL, along with the necessary dependencies. If you're using Python 2, you should be able to simply pip install MySQL-Python. If you have any problems with installation, then please consult the README in the course repository. If you want to use the default Celery executor, you also need to create user Airflow at localhost with password Airflow and give it access to the Airflow database on MySQL. Or you can update your Airflow CFG file in the Airflow home directory with the appropriate name and password. Okay, so now that we have our database initialized, we can start our Airflow front end. We can do so by running Airflow web server. And you should see some startup. And you can navigate to localhost 8080, which is the Airflow default. So we can see all of these different example DAGs. We can also see some DAGs that we'll be using for later videos. So Airflow defines tasks based on DAGs, and each of these DAGs is defined in code. They're comprised of operators, and Airflow gives you many operators out of the box. Operators are broken into three major types: action operators, which perform a particular action with your data or pipeline; transfer operators, which move data in your pipeline; and sensor operators, which tests to determine if a particular state or requirement has been reached. In any particular DAG, you can have a mixture of these types, or just one. In terms of the standard operators Airflow includes, they have a simple base operator, but a variety of other more complex operators with additional methods, attributes, and functionality, including bash operators, HDFS, Apache Hive, many database and cloud connectors. And I notice a few more every time I start a new Airflow project. Given its status as an Apache incubator project, the amount of hook and operators are likely to increase before this video is released. For our purposes, we're going to be using a few of the built-in connectors, including SQLite. We can add them in the admin connections section. So if I go here are all the different connections that are defaults. For example, if you have MySQL running, but you have a different password for the root user, then you can edit it using this. So you'll simply need to set your password. You might want to set a different user. So for our project, I'm going to create a new one. We're going to call it Twitter SQLite. The connection type is SQLite. And the host just needs to be a local file path. So I'm going to put it in my Airflow directory. And you don't need to set anything else. You can just save it. So we can go back to our terminal, and I want to go through a few of the different commands available. So I'm going to open a new terminal, and I can list all of the DAGs by typing Airflow list DAGs. First, I need to be in my virtual environment. And so here I can see it's kind of a view very similar to the one that we just saw in the web server. So a common one to use is this tutorial. So I can list the tasks as a tree by running the list tasks of tutorial. And here I can see that there's a bash operator called sleep, a bash operator called print date, a bash operator called templated, and that calls another bash operator print date. So I can test it using the Airflow test command. And each of these is going to require a date to be passed as a parameter. So I'm just going to pass 10th of October, 2016. And I can see here in line 77 that it has printed out the date. So I can run that same one with maybe a different one of the ones. Maybe this time use templated. And I can see here that it's done a few different commands based on that. So your output won't look exactly like mine because these templates use bash operations to print out the current date. However, if you are able to run them properly, then your Airflow is properly installed and working. Here with the test commands, they're not going to be storing them to the database, but everything else is set up. So to get your worker and schedule actually running, we need to run a few different commands. So we already have the web server running. We can start the scheduler by running Airflow scheduler. And in a new window in my virtual environment, I can also run a worker by calling Airflow worker. So now if I go to my interface and I go to my DAGs, I can actually turn on one of these examples, like for example, the tutorial, and take a look. To call it, I can trigger the DAG. It should, with the scheduler running, it will eventually trigger it, but I can also go back to my terminal and in a new tab, I can Airflow trigger DAG. Since we're not testing, we can just trigger the DAG. And if we go back, we should now start to see it populating. So we can see that we already have 3 successes. And if we take a look at our DAG ID, we can see where it is. We can see how it succeeded. These ones have yet to be scheduled, but when they're running and scheduled, they will change. We can also view the logs. We click on the task and we click on view log. Then we can see our different logs. We can look at the task details. We can even take a look at the code. So as you can tell, there's many more features of this web server. We're going to stop here for now, but you've run your first Airflow pipeline using the tutorial example. Congratulations. In this video, we will cover running a custom DAG with Airflow. If you've installed the video repository, you have all the files necessary to run this workflow. This workflow is an example that takes a Twitter search term and it saves the tweets to a file. Then it's going to move those tweets into a database, and uses some simple data analysis to pull out the most popular links from the tweets. To run this DAG, you'll need authorization credentials from twitter.com. You can set up a simple app and authorize it in a few steps at apps.twitter.com. In the main repository root folder, you should already have a config folder, and in that config, you'll want to set up a file with all of your own Twitter keys. The example config file from the repository will point you to the naming conventions that are used. So here we can see that there's a few globals set up at the top of the file. And again, here's the config file global. It's going to point to the base directory in a folder called config to prod.cfg. Obviously, if you want to change that, it's fine, and you can do so here. Before we run our custom DAG, we're going to take a look at the different tools and review a bit about Airflow architecture in the process. So we can see just from looking at our imports here that we're going to use a few different types of Airflow classes. We have, of course, DAG, which is our primary DAG object. In Airflow, no task exists on their own. They're only found when they're registered to at least one DAG. So obviously DAG is going to be pretty essential to us. We're also importing several operators, here email and Python, and we're importing a hook, which is the SQLite hook. And we'll see a little bit about the differences of those as we go through the file. There's also many other things that we're using. We're using some pandas, we're using Tweepy to search Twitter, and some other standard library things. So if we start looking down, one of the first things that you usually find in an Airflow file is the definition of the DAG. So here we have the default arguments. In these, again, a lot of these things can be set and changed. We have the start date, which is 4 days ago. It's important to note that the start date needs to be either something defined by a datetime object in the past, or it needs to always start at least one interval behind the actual schedule interval. So you'll notice here that I'm using 4 days ago. If this were set to datetime.now, and the schedule interview here down in the DAG was set to something like daily or weekly, then what would happen is the scheduler would call the file every time to see, hey, is now the time that I can run it? And every time it would say that it's starting now. So it would never get evaluated and therefore never run. So it's important to think about a little bit of these architecture constraints and determine what makes sense for your DAG. So our first DAG here is called Twitter links, which is the ID, and we're passing in the default arguments. And here we have some retries again for our arguments, and we also have our schedule interval set to daily. There's a few of these nice little syntactic sugars they give you, for example, once, daily, weekly, things like that. So depending on how you need to run it, you can either specify an exact time interval, or you can use one of their easy at dailies or something like that. So if we skip over the bulk of the logic and scroll down to see the actual operators, you can go through these at a later time. I recommend you do so. It's basically extracting our data, and it's the code that will search Twitter as well as store the files. And we have some conversion to SQLite, and we have some pandas logic. And when we get here down to the bottom of the file, we can actually see declaring our operators. And again, for this, we're using primarily Python operators, but I want to remind you that there's plenty of different operators. There's SQL operators, there's Hive operators, Hadoop operators. There's quite a lot of different operators available. So depending on what your work uses, what your project uses, or what you like to use for fun, you don't have to use the Python operator. You can use quite a few. So here we can see, though, that when we define a Python operator, we have a few different keyword arguments. The first thing that I like to define is the task ID. I tend to keep my task IDs the exact same name as my Python callable because this helps me debug and it helps me remember where the code is. We are also using provide context equals true. This is going to give our task that extra DAG context, which we may or may not need. This is kind of any keyword arguments or arguments that are attached directly to the DAG. I also need to call the Python callable, and this is just the function that is in that same file, or you can import it from another file. Then I'm obviously defining my DAG, because again, no task exists until it's part of a DAG. And here I'm using an extra keyword argument called params. It's just a parameter dictionary that I can pass to my task. The dictionary here has a query equal to hashtag Python. The search Twitter function I'm using as my Python callable value is just going to simply search Twitter with that string. So if we scroll down, we can then see another move tweets to SQLite. It should look very similar. However, this one does not use the params keyword argument. And then I have the ID popular, which is very similar again. And finally, I have the email links. And here with the email links, we can see that the keyword arguments differ. We can see that I need to set to subject HTML content, and I have some optional arguments. Here I'm including files, and this will be a file attachment. Again, to use the email operator, you're going to have to set up some configuration in your airflow.cfg. There's a section around email that is primarily called email and also has SMTP settings. So you need to set that to something, or you'll need to have a mail server running locally and be able to check your local mail. And finally, in these last lines, we can see where we're actually creating the DAG. So up until this point in time, our DAG just existed, but it didn't have any steps. And now when we set these downstream and upstream commands, we're actually configuring our DAG and saying, okay, these tasks happen first, and then they move downstream into these other tasks. So here we can see the simple search sets the downstream of moving tweets to SQLite. Then the ID popular is setting the upstream of the move tweets to SQLite. So we already know now that it goes simple search to move tweets to SQLite to ID popular, and finally email links here, which has the upstream of ID popular. So one other thing that you'll need to change before you run this is you'll want to set the email to your email. So here I do have it set to my email, but here you'll want to set it to your email so that you can ensure that it runs properly. I already have my web server and my scheduler and my workers running. So I can go here and I can turn on my Twitter links. Now this is again set to run daily, which means it likely won't be scheduled immediately. So I can use my same trigger DAG to call Airflow trigger DAG, and that will schedule a run. So now when I return, I can click on this and I can see it starting to run. And I can see that the steps are exactly as stated before. First, it's going to search Twitter. Then it's going to go to CSV to SQLite, identify the proper links, and email the best links. If anything fails, I can get them here, and I can also see the different logs and the steps. So congratulations, you've been able to run your first DAG. I would take time to look through it. If you want to also see where it's storing the raw tweets, you can look in your data tweets directory. And if you want to make a few modifications, I encourage you to do so. One possible thing would be to calculate the most popular hashtags, or to, instead of the links, provide the most popular tweets. Another option would be to add the queries to the files that you're sending so that you know which query was run. Or another possible option is to add a different step. So if you wanted to, instead of saving or sending an email, you could upload that to the cloud, you could upload it to Google Drive, you could save it into a database that you can check later. So there's a lot of different options for even just modifying the simple DAG, or you can step out on your own and create your own first simple DAG with Airflow. Either way, have fun and happy pipelining. In this video, we're going to cover dynamic generation of DAGs using Airflow and covering more complex Airflow operations like Subdags, which are DAGs that are just one part of a larger DAG, as well as branch operators, which allow us to have many different pathways in our pipeline. First, we're going to take a look at more complex tasks that we have from the Data Pipelines course repository. We're going to start by investigating this task in the Airflow graph, and then we're going to take a look at the actual code. So I'm in the code right now. I will switch to my Airflow. And if I go to all of my DAGs and scroll down, I should see this generate Twitter DAGs. And so here we can see the graph visualized. So we can see that we have a few new structures. First off, we haven't had one where it starts out as a linear progression and then it goes to multiple pathways and then it returns back. So we can see that first we have fill terms, and this is if we scroll over it, and we can see here that based on the coloring up here that this is a Python operator. Then we go to a branch Python operator, and this is what's going to set up our branching. So here we can see this generate search terms is generating a few different search terms. And then we see here that the different branches join again with this insert NID pop, which here we can see by color coding is a subdag operator. And that joins them together, and that's going to call a subdag, which again, a subdag is going to essentially be its own DAG and is going to have its own set of tasks, which we can take a look at with the graphs and as well as looking at the Python code. When that subdag completes, we go to email best links, which is an email operator, and then we go to clear latest, which is a bash operator. So let's take a look at the code that creates this DAG. First, we're going to open the main DAG, which is this generate twitter.py. We can see that here we have quite a few operators importing. So again, we are using the SQLite hook. We're using the DAG class. And then here we have a bash operator, email operator, subdag operator, Python operator, and a branch Python operator. We can also see that we're calling in the search Twitter from our Twitter Airflow script, as well as the raw tweet directory. And then we can see that we're calling from this module Subdags, our Twitter Subdag Python script, and importing Subdag directly from there. So if we look through, we can see that we have a global defined as our search terms. We have similar default arguments, and we're setting up our DAG very similarly to our last DAG. I'm gonna skip over looking at all of the code. I highly encourage you to look through it, make sure that you understand it. But here when we start defining our operators, we can see that we have fill search terms here, which is our beginning task. Then we go to generate search terms, which is our branch Python operator. Then we have our email links defined, and we have our subdag operator defined. We can see that the subdag operator here, we have a trigger rule, and this trigger rule can be set for any subdag, and it can be set using the trigger rule class, which has a series of options, or it can be set using a string. So here we're using one success, which means at least one of the upstream tasks has succeeded. So we can see that the subdag here is set equal to the subdag which we called from our subdags module. It's important to note that you need to define your subdags either in a separate directory like we've done here in subdags or with a factory function. This is because if they're defined in the main DAGs folder, then Airflow is going to detect them, it's going to pick them up, and it's going to start running them on their own schedule. So that's fine if you need the subdag to actually run its own schedule. But part of the beauty of subdags is they allow you to kind of create these utilities that you can use across several different DAGs and build them out in a way that you can reuse. And because of that, you probably want them to only be called as a subdag of a main DAG. And again, these are just essentially subgraphs, right? They're just going to perform a series of steps. They can even have branching themselves or different parallelization that you may or may not need. And because of that, though, you can create a folder for them and you could create a series of different scripts. It's a great way to reuse code. Finally, we have our bash operator here, which we hadn't defined one before. And it takes a few different things similar to the email operator. It's going to have some different keyword arguments. So here we can see that it has a bash command. And here we see something interesting. So we have a for loop directly in the main portion of our Python script. So this is going to execute whenever this script is called, which we know Airflow does to determine, is this a DAG that I should be running? And what we have here is we're looping over the search terms, which we've defined globally, and we're removing punctuation, and then we're setting up a Python operator for each of these different search terms. And then we're setting the upstream as the generator and the downstream as our subdag. And here we can see our final ones. So if we look through, this is going to define essentially what we saw when we were looking at the visualization. We saw that it said search Python Twitter, search PyData Twitter, and a few other things. And we can see here that we're using the parameters query equal to the term. So here we can set all of the terms that we want to search Twitter for. You might be wondering why we need to have a Python operator for each of them. And this is because the way that a Python branch operator, or actually it's called a branch Python operator in Airflow works, is it's going to return a string. And that string should match a task ID. So there needs to be a task ID for each possible pathway that the branch Python operator can return. So here we can see our branch Python operator uses generate search terms. And if we look here in our generate search terms, we are essentially returning a random choice from all of the different search term values. So we need to make sure that there's a Python operator or any type of operator that is going to match that task ID. So that's an important thing to note if you're going to use branching. So now we can try triggering this DAG. There's a few things to note beforehand. You'll need to have SQLite 3 installed, and you'll need to have set the email configurations in your Airflow CFG file. And you will also want to set the email address here. So here I'm going to put my main email so I can be alerted when it finishes. I'm going to save that. Then I can go again to my trigger. Here I want to trigger generate Twitter DAGs. So now if I go over and I go to my DAGs, I'll need to turn it on. I can also turn the subdag on. That's fine because it will know that it's a subdag. And I should start to see it populate. And I can look at this tree view. It's a little bit of an easier view because it's going to show me sequentially as each of these are called. So I still, again, have my scheduler and my worker running. I should hopefully see this begin to populate soon. I trigger it again. Feel free to trigger it a few times. Again, this is just going to be saving some of that data locally. So I'm going to try to see if I can see one of these manual runs. And it does say it's running. I'll have to check the logs and see what's going on. It could be that my computer is just not responding properly, but eventually you should start to see these fill up and turn green. Of course, if any of them fail, then you have that fail log, and you can take a look at the logs at any point in time. To get some practice writing your own DAGs, you can begin by modifying this task. You could instead pull search terms from a file by rewriting the fill tasks. We could also have the subdag only execute if all of the previous paths have finished by changing the trigger rule. So this trigger rule can be set either as a dummy operator. It can be run only if something fails upstream. It can be run if only all of the previous tasks have succeeded or all of them have failed. So this is going to mean that each of these pathways need to complete. There are a few ways to go about this, but one possible way is to change our branch operator to use arguments. We can then call our main DAG with each of our search terms. This would essentially be passing it either as an argument or as a keyword argument through our entire pipeline, or at least up until this point. We could also potentially add that to the database, right? A database check of what has not been run yet and run that one and continue running it until all of them have succeeded. Another good improvement would be to have the query also sent with the URLs in the attached file so that the receiver knows which search completed. So here, let's take a look. Okay. If you make any of these improvements, feel free to send a pull request to the repository. I'd love to give you some feedback and see your code and possibly accept it and put it in the repository for others to use. You now know how to build more complex Airflow pipelines, and you should feel comfortable using this code and improving upon it. If you have a pipeline or a set of tasks you'd like to try with Airflow, now's your chance. You know how to write one of a variety of operators. You can use hooks along with the connection database to use local or external sources of data, and you have logs in case you hit any snags. I encourage you to have fun. Hopefully your tasks are starting to turn green. To give you an idea of how this should look, we can take a look at some of these succeeded tasks. And we can see here, if I look at any of these tasks and I take the tree view, then I can start to see how it should look. I can also take a look at the Twitter task that we have running and take a look at that in tree view. So hopefully your tree view is starting to populate, and have fun and happy pipelining. In this video, we'll cover some more complex Luigi options, such as running Hadoop jobs from Luigi. If you already have a Hadoop setup, Luigi is great for integrating those Hadoop jobs into your Python ecosystem. Luigi also integrates well with Scalding and has similar API and setting structure. To get started using Luigi with Hadoop, you'll need to ensure that you have Hadoop and HDFS installed on your server or cluster. Then the main difference is using a separate task class, which requires both a map and reduce statement. As you likely already know, Hadoop is built upon a map-reduce structure, where you first map something with your data, such as a tag or a new value based on your data's schema or structure, or the data itself, and then is reduced or grouped into some aggregate value or sets. MapReduce is great for solving problems that can be done in a distributed and concurrent rather than linear fashion, and it's really famous in large batch jobs. In the repository in the Luigi directory, we have a MapReduce file called word count MapReduce. I have it open here. Word count is a common beginner MapReduce task where we take all the words in a text file and then we count them. It's a good MapReduce example because it's easy to show. Each document is first split into words, and then those words are given counts by the mapper. And then the reducer sums each of those counts based on each word. We'll be using data from IRC or Internet Relay chat logs. The data from these logs is gathered by a bot scraper that I wrote, which you can find on my GitHub page if you're interested in looking at the code. It saves logs from public chat channels in JSON format. So here I have included in the repository a few days of Docker chat room on Freenode. We can put it on Hadoop using the commands we know for the Hadoop file system. So I'm going to go back to my terminal and I can just use my similar HDFS DFS commands. I'm going to make a new directory. I'm going to call it chat logs in my user Hadoop folder. Then I'm going to put my local file. Now I can check and make sure that it's there using my ls command, and I should see it there. Perfect. Now let's check our file and see what our code does. I'm going to go back to our word count MapReduce file. So we can see here at the top that we have some new imports. We're importing Hadoop and HDFS from contrib. Can also see that here we just have a simple Luigi task, and it has a file name parameter, and then it has some input and output. We can see that these input and outputs are HDFS targets, which are new and different. Again, because we're using HDFS as our targets for inputs and outputs, we need to do this when we have a Hadoop task because obviously Hadoop knows nothing of our local file structure outside of HDFS. So if you're going to run a Hadoop job, you need to store it in something that Hadoop can talk to or use a library that helps with that. So here we can see this process chat logs is just a simple pre-processing, and it's going to go grab the messages. Because these are IRC chat logs, sometimes it has info messages of people quitting the channel or people changing names and things like that. And it also has usernames and other structures in the JSON. So this is just going to grab from the JSON the message key, and then it's going to save that to a messages only text file on Hadoop. So now we get into the chat word count, which is a new class. It's inheriting from a new class. And we can see that it's called the job task. And we can see it's already different because instead of using a run command, we have a mapper method and we have a reducer method. And we can see here that our mapper method is intaking lines. So this is going to come from Hadoop, and it's actually going to use Hadoop streaming to stream each line. Then it's going to go through this for you loop, and it's going to yield all of the words with the counts. So here we're stripping extra spaces and then we're splitting. This is a really naive way of looking at word tokenization. And one of my challenges to you is to rewrite this MapReduce using better NLTK tools. And the Python NLTK toolkit has a great function called word tokenize that's going to do a lot better of a job than this is. but we'll use this naive implementation to simply demonstrate. We can see that we need to yield our key and the value. Then those keys and values get streamed into this reducer step, which is going to, again, be another generator because it's using this yield command. And it's going to take each key and it's going to sum all of the values. So this should give us the overall count. We can see that it requires the pre-processing step. And we can also see that the output is another HDFS target. And this one is going to be called word count and also end in txt. There's some logic here around keeping the file names the same. And this is to give you a little bit of reusability. If you want to use this as a base word count class, then you can possibly use it with different texts and you'd only have to replace the pre-processing step. There are a few other things that we need to set, so let's take a look at our config file. This is Luigi config. So as you can see here, we have a main Hadoop section. The client I'm setting actually is the default, so you shouldn't need to set this, but I like to be explicit. This is the Hadoop CLI. You can use other clients if you're using Python 2, but in Python 3, this is currently the only supported one. Then we have the streaming jar file, and I've also defined it as the jar. This is just to help with some discovery problems I was having. For yours, you'll obviously need to set it up to point to the Hadoop streaming file. This should be in your Hadoop lib somewhere. You can also just search your file system for Hadoop-streaming and hopefully it'll come up. Then you need to replace these to point to your local. If you, like me, are using Python 3, then you need to set your Python executable. This is to tell Hadoop that the jobs that you are running need to be run with Python 3. Otherwise, you're going to run into pickling issues and other issues where Python 2 and 3 do not play well with each other. If you're using Python 2 system-wide, then you don't need to worry about this step. Finally, you can see that I have my temp directories, and this is important for streaming tasks. So if you're going to be using this, you also need to set those. So you need to make sure that Hadoop is running. Hopefully you have your name node, data nodes, and yarn in the Hadoop scheduler still running. You can usually start that with start DFS for the name nodes and data nodes and start yarn.sh to start your resource manager. All right, so let's go to our console and get it running. So again, I'm going to just run it the same way. I'm going to set my Python path first. I'm going to pass in my file name. So I'm going to get that running. And now I can go and see it running on Hadoop. I have one of my older applications here, but this will eventually show up in running. And remember, we have the pre-processing step, so this might take a moment in time. So while we wait, there are plenty of more things you can do with Luigi at scale that are interesting, including integrating it into auto-scaling using Amazon and Docker containers as documented in a talk by Adroll. You can also read their details on the Adroll blog. Or you can use integrations for different databases like using Redshift, or determining how you'd like to batch and run your pipeline with backpropagation or self-generating tasks, both of which are documented in the Luigi documentation. I recommend taking a good read through the documentation and trying out some of the tools with your own pipelines. I'm going to really quickly check here and see if it's running. I click again. Yes, so I have my latest one, has not yet finished, so this is still running. And depending on how you have your Hadoop tracking set up, you might be able to track it. I currently don't have my tracking running, but you can better debug Hadoop tasks in Hadoop. So I recommend learning and using Yarn if you're going to be writing Hadoop tasks. So when this finishes, you can use the get command to take a look at the different word counts. Again, I challenge you, this is a very naive approach. It's simply splitting on spaces, which is not really a good way to do a word count analysis. So I recommend and challenge that you both make it a little bit faster, maybe using iter tools to create that first mapping, and that you use NLTK to use word tokenize, and that's going to get better results. You could even do something like removing stop words, because clearly stop words are going to be the largest count. These are things like I, the, he, is, the most common words. So if you need a hint, then there's going to be some solutions included, but I challenge you to find your own solution. And if you get stuck either with this work or any of your conversions into Luigi pipelines or using Luigi with Hadoop, there are plenty of knowledgeable folks via Stack Overflow, searching on blogs, or reaching out to the mailing list group listed on the Luigi project's GitHub page. Have fun, and feel free to also reach out to me if you run into any issues. And I wish you many good Hadoop jobs via Luigi. In this video, we'll be covering an introduction to using Apache Spark, and more specifically PySpark for your data pipelines. If you haven't heard of Spark yet, you've likely been living under a rock. I'm joking, but the project has garnered support, praise, and wide usage since its initial development at Berkeley's AMP Lab in 2009. Spark became an Apache project in 2010 and has since grown in uses, popularity, as well as functionality. We don't have time for an in-depth coverage of Apache Spark, but since it is often used as part of a data pipeline or in conjunction with projects like Hadoop, I wanted to make sure you were exposed to a bit of its functionality. Apache Spark has many different modules for data analysis and machine learning and supports several languages. You can use it with SQL, R, Scala, and Python. The different clients have some different features, but the Python community within Spark is fairly large and has kept the Python interface, better known as PySpark, as one of the most advanced outside of using native Scala. Since you already have Hadoop set up, downloading and installing Spark shouldn't be a problem. I have some extra installation instructions that work well for me in the repository README, but I would highly advise to use the setup instructions directly on Spark's website. You can also look up setup instructions specific to your operating system and the version of Hadoop that you already have running. The main things that you'll need to do as part of the setup is set some environment variables, including Spark Home, add the Spark bin files to your local path, and add your PySpark files, including your Spark download to your Python path, including the py4j files. I have my local PySpark set up so that I use Jupyter Notebook directly when calling PySpark for data analysis purposes. It doesn't matter if you run the code in this video in a Jupyter Notebook like I'm going to do, or in a simple PySpark shell, so it's fine to use the default implementation. If you need time to get Spark installed and set up, I would recommend pausing this video and coming back when you're ready. So I'm going to go to my terminal, and again, I'm in my notebooks folder, and I'm in my virtual environment. Because I have PySpark set up to run Jupyter Notebook, this will start up a Jupyter Notebook for me. And if I go over to my browser, I have my notebook running. So I'm going to clear the outputs for us. Okay, so the first and most important variable that's going to be available to you when you start up PySpark is SC, which stands for Spark Context. So when I run it there, I should see it. If you're running this in a shell, then you should see it as well. Spark Context is the way that we talk to the actual Spark engine and cluster, which is in Java and Scala. Through this context object, we can farm out work to Spark and send data and objects back and forth between Python and Java. This is thanks to the awesome work by the py4j project in conjunction with all of the work that the Scala and PySpark developers have done. Okay, so we now have our Spark context. We also have SQL context, which is stored here as SQL CTX with a capital C. If you're familiar with SQL, you'll be amazed at the variety of commands available with the SQL context operator. We won't be using the SQL context in this video, but I encourage you to take some time and play around with it. It's very easy to query your Hadoop data stores this way, and it operates very similar to Hive. The main data structure Spark uses behind the scenes is resilient distributed datasets, otherwise known as RDDs. We can make one easily using our Spark context. So I'm just going to call Spark context parallelize, and I'm giving it a range and a number of partitions. So we see that we have now parallelized a simple range across 20 partitions. We can grab some of the data using the take command. So take pulls our data into the Python client so we can use and manipulate it. When you're dealing with big data, you can use take to see just a small piece of your data and make different calculations or transformations depending on what you're seeing. We can also load other data like text files into an RDD. I'm going to load some European Parliament speech data I collected for a PyData Berlin hackathon. The code to extract the data is on my GitHub if you're interested, and the speech data can be downloaded following the instructions in the repository's README. It's simply on a public S3 bucket. So here, I could have uploaded this to my local Hadoop. I'm going to load it directly from the file, so I need the full file path. RDDs have many methods available, including plenty that are useful for cleaning and evaluating things like text. In this video, we'll cover using filter, map, and reduce in our text data. Spark RDD transformation operations, which filter and map are some of, are lazily evaluated, meaning the code to transform the data is not called until we perform an action on the transformation. So first, let's filter, and we can find references to any topic. This filter can use any type of lambda, so it can also be used easily with numbers or different data types. So this dataset contains 24 different European languages and speakers of the European Parliament. If you know any European languages, feel free to filter on a different term. I'm going to filter on the German word for Germany, which is Deutschland. So I'm going to filter my text RDD, and I see that what it returns is just a reference to the RDD. And when I call first, it's actually going to evaluate it. So if you saw, there was a slight pause as it was running, and then it pulled the first reference. Every time I reevaluate this filter that I just ran, Spark will call all of the transformations and perform the entire pipeline again. For this reason, it's a good idea to perform your desired transformations and actions once and collect and store the results somewhere. You can also cache or persist the result using built-in Spark commands. So I'm going to set up Germany. I'm also going to search for Angela Merkel, which is Germany's chancellor. RDDs can allow you to create new RDDs by merging other RDDs. There's also some interesting intersection methods available. So here I'm going to create a new RDD of these two RDDs by using the union command. If I take a look at this, I can see I have a union RDD. Now, depending on your data and depending on how large it is, you're going to want to start to understand how this happens behind the scenes. Because what this is doing is going to be, depending on how your data is stored, it may or may not be moving data across the network. It may or may not need to be sorting or sending that data in a different way. So I highly recommend taking a look at how to optimize your Spark implementation. So I can call the count here. And again, that is performing an action on my RDD. And if I would like to essentially cache and persist the data locally, I can ask for it to be persisted. So to take a look at the contents and create a simple bag of words, I can use MapReduce. This will take all the lines as one single line and then reduce by key. So first I'm using the map again, and I'm returning each line with a 1, and then I'm going to reduce by key, which is going to create the summation. And when I run take 10, which again is an action, it's actually going to evaluate and transform. And I can see that I have each line, some of them appear twice. But this isn't exactly what I wanted. So I want to see if you can figure out how to perform a word count in Spark. If you get stuck, I've included a solution in this notebook. One big hint, Spark has an amazing method called flatMap, which performs a map function and returns a flattened array. Beyond what we've shown in this video, there are many different ways Spark can help within your data pipelines or assist in normal data analysis. There are lots of resources from the Spark community and Databricks for learning more about Spark online. In this video, we'll be reviewing how to use Apache Spark Streaming for your data pipelines. Apache Spark Streaming is incredibly popular for handling pre-processing or near real-time processing of streaming data. Similar to other streaming data solutions, this is great if you have a problem you need to react to in near real time, such as advertisement bidding or interactions with consumers on your site. This streaming can also be used for longer windows, somewhere between real-time and nightly batch analysis. Data analysis of these near real-time or shorter than daily windows can help your team make better decisions. You should already have Spark installed. If not, please follow the instructions to do so on the Spark website. For the purpose of this section, I found some great open source code which allows us to turn a Twitter stream into a stream for our Apache Spark. It's included in the streaming folder in the code repository. To run the code, you'll need a Twitter API key and authorization secrets. To get those, I recommend creating your application if you don't already have one on apps.twitter.com, and you can follow the steps listed there to get your key and secret. The script is going to look for these keys in the configuration file, which should be set up as described in the repository README. An example configuration file is also provided in the repository. So let's get started. I'm going to go to my terminal. I'm in my data pipelines course folder, and I can see that there is a streaming file tweepy stream. I'm also in my virtual environment, so I should just be able to run Python tweepy stream. So this is going to start a G event server, which is going to essentially spit all of the streams from the tweepy stream into our streaming pipeline. So I also need to start my PySpark. So I have my PySpark set up again to run a Jupyter notebook. Now that I have both of these running, I can go back to my notebooks. I'm going to use this Introduction to Spark Streaming notebook, and I'm going to clear all the output first for us. Okay, so first we need to import the streaming context, which is what we'll use to interface with our stream. We can also make sure our Spark context is available with the variable sc. So now I have streaming context. My Spark context looks good. Now that we have both, we can create our streaming context object. Here we can set our time window in seconds. There are numerous other configuration parameters we can pass with both our context as well as our streaming context, but they're likely to change over time. So I recommend reading the latest documentation to set these extra parameters. I'm just going to simply create a 60-second window for my streaming context. So here, instead of 30, I'm going to use 60. Then we define our variable lines as our socket text stream and start listening on localhost port 9999. This is where our G-event server is sending these tweets. Now we have a Spark dstream object, which has some, but not all transformation and actions available, similar to RDDs. So now I have my dstream object. If I were to show my lines, you can see that I have my dstream. So now that we have a stream, we can use flat map, which is really handy, and split on spaces. We could also use slightly more complex tokenizing here using the NLTK tweet tokenizer. I challenge you to implement the NLTK tweet tokenizer for homework. Instead of using line split here, you would simply use a tweet tokenizer from the NLTK library. The tweet tokenizer has some great things like being able to pull out ats, being able to split on casual text, and being able to identify URLs and emoji. But we're going to simply split on spaces here. We can create a bag of words using a simple map and reduce, similar to what we've done before in our Hadoop work. By using reduce by key, Spark will automatically collect all of the keys together before using our mapping, which simply returns a count of each word. The reduce operation then sums all of the values of each key to get the total amount of times the word appeared. We can print our minute-by-minute bag of words using Pretty Print, which is available directly on our transformation. Finally, we want to start our streaming context, and we use await termination, which means that it will continue to run until we stop it. So we should start seeing some results pretty soon. If we were using this in our data pipeline, we wouldn't be printing these, but instead saving them or doing extra analysis or cleanup, pre-processing before saving them or sending them further down the pipeline. When using Spark Streaming or any streaming interface, it's important to consider the structure of your data and determine how much parsing, cleaning, and analysis you can or should do before saving or moving to the next step. You don't want to add so much computation or parsing that you build up this backlog and you introduce memory issues into your pipeline. So we see our first time window has completed. Currently, this parser just looks for the word Python. Feel free to also change directly the streaming file, and that can search for whatever terms you'd like to search. And you can even add a whole list of terms. You can add more complex queries. And I'm starting to see some results. So this will keep running as long as you let it run. You can also, of course, stop it or try playing around with saving some of your data. So there are a lot of good talks, tutorials, and very robust documentation on Spark's website which covers good design patterns for Spark streaming. I highly recommend taking a look at that, as well as watching some of Paco Nathan's and Holden Corral's talks, or reading Holden's O'Reilly book for an in-depth analysis of the many use cases for Spark streaming and tips on how to keep Spark fast and efficient. There are many more Spark streaming features, including easy integration with Kafka, Flume, and Kinesis. I hope this brief introduction whet your appetite, and I encourage you to continue learning more Spark for your pipelines. In this video, we'll be taking a look at task-based or pipeline-based integration for Django, called Django Channels. I don't recommend installing Django just to use channels. It's far too heavyweight and it's primarily a web framework, and it's not really intended to be used as a pipeline. However, if you're using Django for your website already, then integrating your tasks or pipelines using Django channels might make sense. To note, Django also supports Celery integration using the Django Celery module. Django Channels is a relatively new feature, introduced in Django 1.8. It offers the ability to integrate a WebSocket server or asynchronous server into your Django project. In terms of how we would use a Django channel as a pipeline, the Django channel can essentially be used as a task queue with consumers listening on a particular channel. It can also be used to send data from your web application into a different pipeline. To note, channels should not be used to maintain state or ensure persistence. Django channels will not retry failed tasks or ensure that they finish properly. For this reason, it might not fit your needs depending on the importance of your data accuracy and completeness. The main focus for channels is the ability to create a pub sub or publisher subscriber type of data flow. We'll be taking a look at an example of integrating alerts or chat on the Django site using the Django Channels example repository. So we're going to use Andrew Godwin's Channels example repository, shown here. Here's my fork, which you can look at for the solutions or the code that we're going to do today. But it is directly from Andrew Godwin's, and he has the multi-chat setup, which is what we'll be using today. So you should download and install this repository. He has documentation in the README of how to get all of the requirements installed. You'll also need to have Redis running, and you'll need to follow his example to set up your super user and migrate your database. So we're using this multi-chat example, which allows you to set up chat rooms and lets users message in the chat rooms using WebSockets. For the purpose of showing the pipeline use case, we're going to be creating a log channel that logs all of the messages sent to the other channels. So for example, you could use this and actually pipe this information into somewhere where you're going to store logging of your web application or different things that you're using channels for. So I'm going to go switch and turn on my Django server. So here I have Redis running already in the background, which I'll need to do. Then I can use the simple python manage.py run server from the multi-chat folder, and that's going to start it up. I can see already that I have channels listening. If I take a look at the code, I'm going to start by taking a look at the settings.py, which is where Django stores all of the core settings. Here I can see that in the installed apps, I have both chat, which is the chat folder here, and I have channels, which is installed. And if I go down here, then I can see that there's different channel layers. So I can see here that we're using ASGI Redis. ASGI Redis is a Django project that uses Redis as a backend for ASGI, which stands for Asynchronous Server Gateway Interface. You can use a few different backends when using Django channels, but this is the current recommended and the most supported one. We can also see that routing points to channel routing, which is available in the routing file in the multi-chat folder. So we're going to take a look at that file. So we can switch to the routing file here. We can see that channel routing is simply a list of includes, and that this is going to include the routing file in our chat folder, both the custom and the WebSocket. So if we go take a look at that, that should actually tell us a little bit more about our routing. I'm going to go here to this routing. I can see that I have this WebSocket routing, which is defining some routes that are some basic WebSocket actions: connect, receive, and disconnect. And it's linking them to 3 different functions: WS connect, WS receive, and WS disconnect. When I look down here at the custom routing, I can see that I have here everybody listening on chat receive. but I have 3 different methods. Now, the way that this is able to be done is they are switching based on this command. So this command, whether it's join, leave, or send, it will imply different actions. So if the command says join, it will go to chat join, and so on. If you have just downloaded from Andrew Godwin's, you won't see this last line, and so you'll need to add it. This is where we're adding the chat logging. So I have a new route called chat log, which is going to the chat log function. If I scroll up here, then you'll also need to add it to the import. So all of these are importing from consumers, which is where you define the consumers for your channels. So we're going to take a look at the consumers file. There's a lot in here, so I recommend reading through it more slowly when you're done with this video. But essentially, it allows for the sockets to send different information. What I want to point out here is in WS receive, so this is happening anytime anybody sends a message, the WebSocket is receiving. We can see here that it usually just echoes the payload or the message to the chat.receive. I am also asking it to do so for the chat.log. So I've added this line here, which is going to then also relay that information to the chat.log. When I scroll down here, I recommend again taking a look through these join and leaves and sends, but I can see in the new chat log function that I am creating or getting a new room called the log room. I'm going to set up a log message and give it some basic information. I know that it needs this information to display things because I looked through the other methods available and I saw that they were using a particular set of keys in their messages. So that's where I knew to use room, username, and message type. Those are all for the front end so that they display properly. Then I am getting the chat room that was used in the message, and I'm creating a readable message saying, this person joined this room or this person said this thing in this room. Finally, I'm using my room, which is the log room, and I'm using the WebSocket group attribute, which represents a group object, and I'm sending the log message. Again, there's a lot more on these topics in the documentation, but for now you just need to know that these groups are related to different chat rooms. So using the WebSocket group attribute ensures that I will send to the clients that are connected to that particular room. So now that we have this, I'm going to go back to my web server. I'm going to go to my admin. And if you want to follow along, you should have your user set up and maybe a different user as well. So I have KJAM here set up, and that is a staff user. That's my super user. And I have Sandy here set up. That is not a staff user. If I go back, I can also see that I have some rooms set up. So here I have a log room. You don't actually need to set that up. It'll be created, but you can if you want to follow along. The Python chat room and the staff chat room. So if I navigate directly to localhost 8000, I can see all the different rooms. For the purpose of showing the example, I'm going to open up log room. Then I'm going to open up Python chat. And we can already see the chatbot is working in the log room. We can see that it's sending the messages. If I want to show an example of it working with 2 users, I can open an incognito window. I'm going to log in with my Sandy user. Of course, I cannot join the staff chat, but I can say some things in Python chat. And if I go back to my other browser, then I can see that my Python chat room is functioning similarly, that my log room is still logging, and that I can still read the normal chats. So this is just one small example. If you want to see some others, channels, projects, I recommend checking out the documentation, as well as other examples in the channels examples repository. There are a few implementations listed on the channels project documentation that handle calling of asynchronous tasks. So if you specifically want to use channels for tasks, I recommend taking a look at them first. There's also Slack integration called Django Bot that looks pretty simple if you want to use channels to integrate Django into your Slack setup. So I hope this gave you the first kind of idea of using maybe a more pub sub style to move data or to translate data in a way that works for your pipeline. And I do hope that you continue to read through the Django Channels documentation. And if you're using a Django site, that you can utilize the things in this video on your new site. So far, we've talked about a lot of major pipelines, including larger projects like Spark, Airflow, and Luigi, and smaller task-based managers like Celery. In this video, I hope to give you a glimpse of the distributed task and data pipeline projects outside of these major ones. As you can imagine, I can't cover all of them here, but I have tried to pick out several interesting ones and describe how they operate. I'm sure there will be even more created after the release of this video series, so I encourage you to always keep an open mind when hearing about new projects and take them for a test drive to see if they might fit your needs. The basic tools, techniques, and architecture you learn throughout this series should be useful when applied to newer implementations of these topics. So I think you can take your learnings outside of the particular frameworks and apply them to new projects, new implementations, and new strategies. To give you an idea of how many data pipeline tools there are out there, I found this list, which is an awesome pipeline GitHub repo. And just a quick scroll shows just how many different workflow tools are described in one list. Of course, plenty of these are not in Python, but several of them are. If you know other programming languages or are interested in learning a new one, there are examples in these implementations and in this list that might meet both your project's needs and the language you'd like to use. So the first framework that I'm going to present is Pinball by Pinterest. This is an open source data pipeline, or what they refer to as a workflow manager. Pinball is often mentioned alongside projects like Airflow and Luigi, and it's built on Django and uses MySQL as a primary data store. It ships with its own UI, scheduler, workers, and master process, which can somewhat be compared to Hadoop's Yarn. Each of these tools run as a separate Python process via the command line. Pinball currently only works with Python 2 and doesn't have extensive documentation, so those are two large cons against using it, in my opinion. That said, they do have integrations for pulling data from S3, Bash, Hadoop, Hive, and a service called Qbowl, which is a cloud-based data processing service. So you can take a look here, and it's quite possible they might update it for Python 3. The next project is started at Harvey Mudd University and is used for building workflows in bioinformatics. It's called Cosmos and is available on the project's Harvey Mudd page, but also via GitHub. Here's the GitHub and the latest rendition, which is in beta. It's pure Python. It's only Python 2 at the present and allows you to build simple DAGs in a script. Again, I mentioned it's in beta, and so the functionality might change on the release of the next paper. The documentation is extensive and well maintained. There are many code examples showing you how to build DAGs and use simple Python functions. I'm not involved in scientific data, but they have extensive documentation on integrating things like tumor matching data types or genome matching. So if you work with scientific data, I recommend checking it out just for those reasons. A similar library out of the UK called Rufus is available, which is also developed for bioinformatics use cases. It uses decorators to create simple workflows and has visualization options using GraphViz, so you can output your diagrams or your DAGs into different formats like SVG or PNG. Rufus supports Python 3 and has fairly extensive documentation. I'm here on the documentation site. It also has great examples for using computational workflows. It primarily uses decorators to define the different ways that you want your workflow to work, including splits, transforms, different merges, and managers. If you're using Python for science, Rufus might be a good pipeline tool for your problem space. JobLib is a powerful tool for parallel operations. It's most similar to Dask out of all of the libraries we've covered. It has great documentation and works in Python 3. There are some use cases for caching and persisting data or computations. It can essentially cache output of a method based on the inputs. So it's great for longer running methods or functions where you only want to run it once and not again if the input doesn't change. And these are easy to persist with just a simple function decorator. The documentation has many NumPy examples, so if you're dealing with data in NumPy and want an easy way to parallelize, I can recommend it. And I've used it myself for persisting large arrays and have found it very easy and intuitive. PyScoop is a project for scalable pipelines on distributed systems using pure Python. It has good documentation and works with both Python 2 and 3. PyScoop can also utilize HPC or high-powered computing clusters and has examples of how to implement workflows for problems like the Monte Carlo problem. If you need simple and straightforward parallelization with options to create subtasks on a distributed load-balanced system, I recommend taking a look at Scoop. Finally, if you want something like Celery but lighter weight, I recommend Python RQ, which is a lightweight distributed task queue. It has some of the same features as Celery, including decorators to mark tasks, which are called jobs in RQ, and it uses Redis as its message store. It even allows for simple dependencies between tasks. You could define most of your configuration using a simple config file and get workers and tasks running via the command line. If Celery seems like too much as far as settings and installation are concerned, RQ is a good solution. There are many more projects I wasn't able to cover in this video, so I encourage you to stay curious and keep looking and learning. I hope you're able to apply the concepts you learned in this series to your pipeline problems, no matter what library or language you choose. In this video, we're going to cover how and why to test your Python code. If you're already a seasoned Python developer and have written many tests, you can likely skip this video. However, if you're new to Python or haven't written many tests, I recommend you stay tuned. First, we'll cover what are tests and why you should test your code. Tests come in many different flavors and cover different topics depending on their use cases. Most often, when we refer to testing, we're talking about unit tests. Like the name suggests, these tests aim to determine if a particular piece or unit of code is working properly. There are some other tests we might use in data work called integration testing. This allows us to determine if the different pieces of our system or pipeline work well together. There are also several other types of software tests and user tests, but they aren't as applicable for our data work. Now that we know what tests are, we can talk about why we write tests. We write tests so that we know when we accidentally break things. We write tests so that we don't need to remember what our functions do later from our own memory. We write tests because we don't want to deal with after-hours error messages or PagerDuty. We write tests in case other people break our code, and we write tests even if they are imperfect and need to be updated, because at the end of the day, they make our lives easier. Now that we know the what and whys of tests, we can cover some basics for Python testing. Most Python testing frameworks are built upon the simple built-in standard library testing library called unit test. Even if you don't use unit tests, it's good to know a bit about how it works. With unit tests, you can build a class and write out your tests as methods. Usually you will do this either in a test folder in your module or in a test folder in the entire repository. So we'll take a look at the example of unit tests and cover a little bit more about these asserts and setup and teardown. So I'm going to go to my test stock tasks, which is in the Celery app folder in the repository. Here I can see I'm simply importing unit test. I see that I have this test stock info class, which is going to inherit from the test case. And then I have two methods here. I have setup, which uses this syntax always. And here I'm setting up a few different variables, a start date, end date, and a stock that I'm going to use in my tests. Then I just have a simple test of get stock info. This is the get stock info task in the task.py. And I'm going to pass the information that I set up in my setup and then use a variety of asserts. So here I can see the assert is instance. That's going to test is instance. So it's going to see if the result is a string. Then I have assert in, which is going to assert that high min is in the keys. Then I use assert equal to ensure that the stock is the proper stock. And I assert that the price is a float and that it's greater than 0. So if I wanted to run this, I would go to my terminal, clear and maximize, and I can simply call Python module unit test, and I can see that it ran one test and it was okay. Because I'm using verbose, I also have this pandas data reader error, but that doesn't concern me. So if we wanted to see a failing test, we can go back and actually change one of these tests. So I'm going to assert the price is negative. And I'm going to save that. Now, if I go back and run my tests again in terminal, I see that I have a failure. And I also see that in the traceback, it's going to tell me which test failed, and it's going to give me an assertion error. So this is really useful. Moving on from unit tests, there's also other libraries for testing. So unit test is just the built-in one. There are several different frameworks with some nice add-ons. My favorite is called PyTest. I think PyTest is great because it allows you to write really simple Python code without a lot of boilerplate. It also has some great decorator features allowing you to easily feed in different cases into your method. So if we were to write the exact same test using PyTest, go back to Atom, and this is the PyTest stock task. We can see that it looks nearly the same. We're testing quite a lot of the same things, but it's just simply in a Python function. And we're just going to use the built-in assert to do the testing for us. Let's go to our terminal and use PyTest. I'm going to clear. So you might need to pip install PyTest. And so we can see that it collected one test. We can see where it collected it because it's going to look for tests anywhere. This dot represents the one test that passed, and it passed in a little bit over 1 second. So if we take a look and again break our test, this time I'll say price is equal to 0, and we run it again, we see that instead of the dot here, we get an F. That's for fail. So PyTest will keep running other tests in case we want to test the complete suite and we just want to see all the failures at the end. And then at the end, it's going to say, okay, I'm trying to assert that 28.18 is equal to 0, and obviously that's not true. So you can see that it's slightly different. I feel like PyTest is a little bit easier to understand, but again, it's good to know a little bit of both. When you're testing, you might want to think about mock services or mock objects. You might ask me, what is mock? Mock in terms of testing is when we create a fake service or object that mocks or mimics what we might expect. We can use mock objects or services so that we don't need to do things like test third-party libraries. For example, in the test that we just used, the data reader relies on the Yahoo and Google Finance APIs. We could mock the responses of those APIs so that we aren't actually testing if the API is working. The mock library in Python helps us do this easily, and there are several other mocking libraries depending on your needs. Along the same lines as mock, you might want to use fixtures. Fixtures can set up data or objects before the test suite begins. It's kind of like that setup for the unit test. This setup can, for example, initialize a database that you will use during the test or generate files for a test. Similar to mock, these fixtures are not permanent and can be cleaned up and thrown away at the end of testing. Most Python testing libraries have their own methods of defining and using fixtures. So this is just one code example of the PyTest way of defining fixtures. They have some great documentation on it. There's also some great documentation depending on what you need to build your fixture around. So the main advice I can give you is just to get started writing your tests. There's nothing more difficult than adding tests once you have 30,000 lines of Python code. So take the time to write unit tests now, and don't forget to update them with more examples as you find bugs and fix them. In this video, we'll be taking a look at a library that is useful for data unit testing called Hypothesis. Primarily developed by David McKeever, Hypothesis lets you quickly determine edge cases with your unit tests. Similar to Haskell's Quick Check, Hypothesis allows you to create property-based tests. With Hypothesis, you can be assured that your code has been tested well, as it helps anticipate and generate these odd edge cases. This can be useful particularly with data unit tests, as the data you anticipate is rarely the data you see. Another great Hypothesis feature is that it has built-in support for both Fake Factory, which is great for generating things like fake names and addresses, and NumPy. It also has the ability to integrate with datetime. Each of these libraries can help mimic the data in your pipeline. As long as you have created your code with discrete units rather than long methods without clear beginnings and ends, your testing with Hypothesis, or whatever testing framework you choose to use, will be clear, concise, and easily updated. Hypothesis operates first by generating random data that fits the parameters that you give it. If a test fails, it will shrink the data and retest until it gets the most simple example of your failing test. To help speed up your tests and limit memory usage, it starts with simple data and then gets more complex. Since Hypothesis is generating the examples for you rather than you hard coding them, you need to think about good data that matches what you want. Hypothesis gives you a lot of options for these, including sampling, min-max values, or lambdas to generate data. When it finds a failure, it will show you the data used, even for complex tasks. So let's look at a simple test with Hypothesis. This is going to test some code in our Celery module, and it's this calc ratio. And I can see that, thankfully, I've written a doc string here, and it's going to take in two floats and return a float, and it calculates a ratio of those and converts it into a percentage. So now I'm going to go to Jupyter Notebook, and I'm going to make sure that it can access my tasks. So here I've written my first hypothesis test. I know that I have floats. I'm going to have two different floats. I'm going to pass them here, and then I'm going to use them. And I want to make sure that what I get is a float. I think probably between negative 100 and 100 is good. And I want to make sure that the rounding works. So I want to make sure that indeed I have a whole number and a decimal, and I want to make sure that I have two decimal places. Now that I have my test defined, I can run it, and I immediately get a falsifying example. So this falsifying example is with 0 and 0. This made me think a little bit about the data. So I did a little bit of research, and I found out that a stock cannot be listed if it has a price of 0. Not a big surprise there. The standard minimum value for the New York Stock Exchange is 4. So I'm going to use the hypothesis minimum value to try and run this again. Run my test again. Aha, and it finds a new falsifying example that's using 4 and 4. And I can see that the test that failed is this string ratio. So I'm going to take a look at what this is. And I see because it's 0, it only shows one decimal place. It's just standard Python way of representing only 0 in a float. So I'm going to update my test, and now I'm going to say is less than or equal to 2. So now when I run this again, I can see that I get a new falsifying example. And this falsifying example, these two, and the assertion is that it's between negative 100 and 100. So if I actually run the function, I can see that I get 100.01. And yeah, I had an incorrect assumption here. I thought, there's no way that a stock is going to increase or decrease by 100%, but that is quite a valid thing that could happen. I actually removed that test. Now I'm sure it will pass. And actually, no, it doesn't pass. It's going to give this massive price and a small comparison price. And if I run that, I can see that this is a very large number, and therefore all of my assertions in terms of it being a float that I can look at with the string are wrong. I did a little bit of research on the maximum values of stocks on the US stock market, and generally they don't go above 10,000. They have never gone above 10,000 at this point in time, so I updated with some maximum values as well. And now if I run my tests, I can see that it passed. So as demonstrated, Hypothesis is really great at finding edge cases you didn't think about and helping you think differently about what data you should really expect and if you need to change your code to handle these edge cases. With our stock data, the real-world values allowed us to create passing tests. But if we had more randomized data or data that had a larger range of possible values, Hypothesis can help us find broken parts of our code and logic. In your entire data pipeline or system, property-based testing like Hypothesis won't necessarily replace your unit tests. And we haven't even been able to cover half of what you should be doing as far as testing. For your data pipeline work, you'll also need to do integration testing, ensuring that all of the parts of your pipeline work together. If you are using Airflow or Luigi, you might want to have a few test cases where you know the intended outcome and actually run that test data through the pipeline and see if it's working properly. You might also want to test for failure, and you might want to purposefully make something fail and see if it operates how you want it to. My overall advice is to make sure you have good coverage of your pipeline and keep on writing tests. Congratulations, you've finished. You should feel a bit more comfortable working with data pipelines in Python. If you hadn't ever touched data pipelines, I hope we covered what you need to get started. If you are already familiar with workflow tools in another language, I hope you feel comfortable using Python when it fits best. If you enjoyed the course, I'd appreciate a positive review. I'd also love to hear feedback, both positive and negative. Since this series is over, you may be asking, hey, Catherine, what's next? I have a few suggestions depending on what stood out to you while working through this course. If you have a particular tool you really enjoyed working with, I suggest starting with that and applying this tool to a current problem, something that either you can identify or something you identify with colleagues. Start the repository today and dedicate at least 3 hours a week to it. If it's for work, dedicate at least one day of the week to the project. Your colleagues should support you in developing your skills and helping build something useful for the team. If you had a particular tool you found frustrating or perplexing, I recommend spending some time with it. I often read through documentation from beginning to end, like a technical novel, sometimes with my terminal so I can run the example code while I read. It may seem counterintuitive to go back to bits that frustrate or confuse you, but I actually think that helps you grow as a developer and architect. Why did the authors choose that design? What about the particular class or method or architecture is confusing to you? By trying to see it from the author's viewpoint, you're stretching the way your brain expects to see things built. I believe this builds code empathy, where you can see many possibilities and ways to solve the problem. Having this greater empathy for other people's code can make you way more enjoyable to work with. You can also simply take the building blocks we've learned and apply them to something new, or cover something that we didn't have much time to cover. Speaking of Spark and other systems that you might want to learn, you can take time to learn more about Java and Apache integrations with Hadoop. There are tons of materials available for this, so focus on ones you find accessible and relevant. You can learn a bit more about the internals of these systems, including some reading on the Java Virtual Machine or JVM, or distributed system architecture. I would recommend taking a look at Hadoop and Yarn, but also things like Mesos, which is another way to run a Java distributed cluster. Alongside learning more about Apache Spark, I recommend learning Kafka, a streaming service for Apache, and Hive, a SQL service, an interface to Hadoop. If this video service was your first introduction to systems administration, I highly recommend taking time to learn more about system optimization, monitoring, and performance. I covered many tools to start with in my SysOps video, but that barely scratches the surface. Taking a longer read or study into systems administration and optimization will help you immensely when scaling data pipelines. I can recommend Tom Limoncelli's Everything Sysadmin blog and books. As there are many courses available for learning systems administration, I would start with the systems you are most comfortable with and have access to. If you work at a place that uses a particular operating system, such as Linux, Windows, or even a particular Linux flavor like Debian or Fedora, focus on that system first. It's a good way to learn basic concepts which are applicable to all systems and get some quick gains in terms of your experience and contributions at work. Even if you rely on a systems team, understanding the problems they face when working with your code will make you a more valuable person on the engineering team. Finally, stay curious and have fun. Thanks again for spending some time with me, and I wish you many successful days as a data pipeline engineer.